Hi everyone, welcome to Go Classes. So in this lecture, we will start the next topic, a new topic that is countability. In this topic, we will study what are countable sets, what are uncountable sets. Okay, so this is a new topic and a very interesting topic. Let me tell you. Okay, you will see this that you will find this topic very interesting. The proof, every proof that we will see in this chapter, that is very interesting proof. Okay, so we will discuss everything about countability, all the variations, all the gate, all the previous year exam questions, everything we will discuss in this countability chapter. Okay, so let's start with this chapter. So before we start this chapter, let me discuss the prerequisites. Okay, so what are the prerequisites before learning this countability? What is countable, what is uncountable set? So before we study this, what are the prerequisites? Let me tell you. The prerequisites are function, bijection, injection, surjection. All these concepts we have seen in our discrete mathematics course, right? Yes or no? We have seen what is a function, what is bijection, what is injection, what is surjection, what are the relationship between them. Okay, so everything we have seen in our discrete mathematics course, you can check it out. But whatever we need in this chapter, in this countability chapter, whatever we need, I will discuss it here. Okay, so you don't have to worry. Whatever prerequisite we need in this countability chapter, let me discuss that. So I will quickly discuss all these things. Okay, I will tell you the definition and some examples of all these things. So let's start. Let's start with the function. What is a function? Do you know the definition of a function? The function. So you can easily notice if you have a set A and let's assume you have a set B. So there are two sets. Then what is a function? Function f from A to B. From set A to set B. This function f. This is your function f from set A to set B. Let me tell you, function, that is basically a mapping. Another name of function, that is a mapping, or you can call it, this is transformation. Okay, so these are the different names for function. You can call it mapping, you can call it transformation. What this function does, this function basically, it will transform every element of A into unique element of B. Okay, so this is what this function will do. Remember, this set A, this is called domain of this function f. This is called domain of f, domain of this function f. And what this B is called, this is called codomain of this function f. This is called codomain of this function f. Now what this function will do, this function will basically, it will assign every element of A, it will assign to unique element of B. Okay, so see, this is what this function will do. This function, this is a function from set A to set B. In this set A, you have some elements. Okay, some elements you have. Now in this set B, you have some elements B1, B2, and so on. Now what this function will do, it will basically map every element of set A to unique element of set B. Okay, so this element, it will map to unique element. Remember, you cannot do this. Yes or no? You cannot do this. Very simple point, that for every element of set A, whatever element you take in set A, for every element of domain, what will happen? There will exist a unique element in set B. Okay, so there will be unique. Okay, there will be unique, I can say there will be unique mapping in set B. Okay, there will be unique mapping in set B. So remember, every element of set A will have a unique mapping in set B. Okay, so for example, this A2 can map to maybe B1. Okay, that is fine. Okay, A2 mapping to B1, that is fine. For example, maybe this A3 is mapping to B2, that is fine. Okay, so you can notice every element of set A that is mapping to unique element of set B. Is this clear? This is the definition of function. So very simple, you can easily notice that from what this function will do. Function is a mapping such that every element of the domain is associated with exactly one element of the codomain. Okay, so this is the definition. Function is a mapping such that every element of the domain is associated with single element of codomain. Okay, so you can see if this function is from set A to set B, then A will be called domain of F, and this set B, that will be called codomain of F, and we indicate like this. Okay, so this is the simple topic. You can see the definition of function, that is very simple. So remember, if you have this type of thing, let's assume you have function from set A to set B. Okay, and let's assume that this happens, that for this element A, the mapping is B. Okay, for this element, remember, this is a function from set A to set B. This is a function, this is a mapping from set A to set B. Now, if this happens that for this element, the image is B, then what we will say? We will say that image of A, we will say that image of A, that is B. Okay, or I can say that f of A that will be equal to B. Means, remember, this f is a transformation. Remember, this f is a transformation. This f is a transformation. So what this f is basically doing? This f is basically doing like this, that in this f, if you give A, if the input is A, then the output will be B. Yes or no? If the input is A in this function f, if the input is A, then the output will be B. Okay, I can say image of A is B. So this is the point. So this function, this is a transformation. What it will do? It will take element of A and it will transform into unique element of B. So this is what this function will do. So whenever you have a function from A to B, remember this point, this function is also a transformation. What this function will do? For every x belonging to A, this is what it will do. Okay, this function, what this function will do? This function will do like this. For every x belonging to the domain, okay, for every x, for every element belonging to the domain, okay, what this function will do? It will give a unique output. It will give a unique output. So remember, this will be unique. This will be unique. Okay, so means I can say in this situation, we will say that f of x that is equal to y. Okay, means to this function, if you give the input as x, if this is your input as x, then this y will be the output. Okay, so I can say that image of x that is y. Okay, so very simple point. So this is the definition of function. Remember, this is fine. Okay, in a function, if this happens, that is fine. For example, let's assume you have A, B, C, and let's assume you have 1, 2, 3, 4. Okay, remember this point, that this is completely fine. For example, A is mapping to 1. Okay, means the image of A is 1, the image of B is 1, and the image of C is 4. This is also a function. Okay, remember, this is a function. This is a function. In this function, you can notice that image of A that is 1, image of B that is 1, and image of C that is 4. You can notice every element has unique image. Yes or no? Every element has unique image. Means in this function, if you give input A, then the output will be 1. In this function, if you give input B, output will be 1. In this function, if you give input C, then the output will be 4. Okay, so this is also a function, no problem. Okay, this is fine. This is perfectly fine. So what is not fine? Tell me. This is perfectly fine. You can notice. So what is not fine? For example, this type of thing is not fine. Yes or no? This type of thing is not fine. For example, this is not fine. Now I can say this is not a function. This is not allowed in a function. Okay, I can say this is not allowed in a function. Because of this situation, I can say this is not a function. Okay, because you can notice to this, whatever this transformation or whatever is this f, in this f you can notice if the input is A, then the output is what? Tell me. Then the output is what? Then the output is not unique. Yes or no? Output is not unique. So I can say this f is not a function. This f, this is not a function. Okay, this f, this is not a function. So remember, this f is not a function. Very simple point. Okay, because this type of thing is not allowed in a function. It is not allowed in function. Okay, this is not allowed in a function. So very simple definition. The definition is quite simple. So this is not allowed because you can notice here, this element of the domain, let's assume this is set A, set B. This element does not have unique image. This element does not have unique image. Okay, you can see this element does not have unique image. Very simple point. Okay, now let's see this one. For example, is this allowed? Tell me. Is this allowed? Is this a function? Let me know. Is this a function? Tell me. Is this a function? This is also not a function. Okay, this is also not a function. Why this is not a function? Why this is not a function? What is the reason this is not a function? Because this element does not have any image. Okay, remember, this element does not have any image. For example, in this function, if the input is C, then there is no output, right? Then there is no output. Then there is no output. So in this situation, I can say this is also not allowed. Okay, so this is also not a function. So the point is very simple. The point is very simple. Every element must have a unique image. The point is very simple. This is the final point. If you have a function from set A to set B, this is your set A, this is your set B. Remember, the point is very simple. Every element of A, if you have these elements in A, okay, and let's assume these are the elements in B, then remember this point, every element of A must have, so unique image in B. Okay, this element must have exactly one image in B. This element must have exactly one image in B. Every element should have exactly one image in B. This element must have exactly one image in B. Okay, this element must have exactly one image in B. And similarly, this element must have exactly one image in B. Okay, so this is the idea. I can say this is a function. I can say this is a function. Okay, so this is the definition of function. Every element of domain, this is the domain. Every element of domain should have exactly one image. And this is the codomain. This is the codomain. Okay, so remember, every element of domain must have exactly one image in codomain. Is this clear? Very simple point. Yes or no? So this is the definition of function. So you can see a function, basically that is just a mapping. Okay, what it will do, it will associate every element of domain to unique element of codomain. Okay, so this is the idea. Is this a function? Tell me. This is a function. This is from domain to codomain. In your domain you have 5 elements. In your codomain you have 3 elements. Is this a function? Please tell me. Yes, this is a function, right? Yes or no? You can check it out. This is a function. So you can easily notice this is a function. Okay, this is a function. You can easily notice. Okay, here you can notice this is the domain. Remember, this is the domain. The domain has 5 elements, and this is the codomain. Codomain has 3 elements. Okay, this is a function. You can notice, because every element of domain has a exactly one image in codomain. Every element of domain is mapping to exactly one image, exactly one element in the codomain. Okay, you can see. What about this? Is this a function? Please tell me. Is this a function? This is the domain. This is the codomain. Is this a function? Yes, this is also a function. Yes, this is also a function. You can easily notice every element of the domain. For example, this element, every element of the domain has exactly one image in the codomain. Every element of the domain is associated with exactly one element in the codomain. Every element of the domain has exactly one mapping in the codomain. Okay, so you can see this is also a function. Is this a function? Is this a function? Please tell me, is this a function? Yes, this is also a function, no problem. You can notice every element of the domain has exactly one image in the codomain. This element also has exactly one output. This element also has exactly one output. Yes or no? So very simple. This is also a function. What about this? Is this a function? Is this a function? From this domain to this codomain, is this a function? Please tell me. No, this is not a function. Why? Where is the problem? Where is the problem? This is the problem, right? This element has more than one image in the codomain. This element has mapping, I can say, more than mapping to more than one element in the codomain. Okay, so very easily you can see that this is not a function. Because of this, this is not a function. So remember, every element of the domain must be associated with a single element in the codomain. This must happen. Yes or no? You can see this. Every element, these things are very important. These things are very important. Every element of domain must be associated with exactly one element in the codomain. Exactly one element in the codomain. Okay, very simple. So I can say this is not a function. Yes or no? So you can easily notice here, this is not a function. I can say this is not a function. What about this one? So okay, this we have already seen. Now let's see this one. What about this one? Is this a function? From this domain to this codomain, is this a function? No, this is not a function. Why? Why this is not a function? Because this element has no mapping. This element has no mapping. Yes or no? This element does not have any mapping. Okay, so simple point. Remember, simple point. Every element of domain must be associated with exactly one element of codomain. Every element should have exactly one element in the codomain. Every element should have exactly one image. Okay, so you can see this element does not have any image. So I can say this is not a function. I can say this is not a function because this element does not have any. This element is not associated with any of them. Okay, what about this one? Is this a function? Yes, this is a function. This is perfectly fine. Okay, this is perfectly fine. This is a function. Every element has unique image. Every element is mapping to unique element. So you can see this is perfectly fine. Now let's move on. Now let's see what is injective, surjective, bijective function. This topic. Okay, when can I say a function is surjective? When can I say a function is injective? And when can I say a function is bijective? So let's assume you have a function. Okay, so let's assume you have a function f from A to B. from set A to set B, you have a function f. When can I say this f is injective? Tell me. When can I say this function f, this is injective? Injective. Another name is one-to-one. Another name is one-to-one. Okay. So these are the different names. You can say it is injective. You can say it is one-to-one, or you can say it is injection. So tell me, when can I say a function is in this function f from set A to set B, this function f, when can I say this is one-to-one, or I can say injective? This function is injective if and only if you take two different elements from the domain, then they must map to two different elements of codomain. Okay. What must happen? Very simple. If and only if for all A, B in the domain, what should happen? For every element, for every two elements, if they are different, if A is different from B, then what should happen? Their images also must be different. Means different elements have different images. Yes or no? Different elements have different images. Is this clear? Please tell me. When can I say this function is injective? This function is injective if and only if whenever you have two different elements, then their images also must be different. Okay. The same thing I can also say like this, that for every two elements, if their images are same, what should happen? These two elements, if their images are same, then what should happen? Then they also must be same. If their images are same, then they also must be same. See, what is the idea to remember this injective function? See, this injective, this comes from injection, right? How can you remember this injective function? Let me tell you, trick to remember. If you want some shortcut to remember, trick to remember what is the definition of injective function. How can you remember? Trick to remember what the definition of injective function. Definition of this injective function. What is that? Injective function. Remember, injective function is also called injection. Injective function, that is also called injection. That is also called injection, right? Okay. That is also called injection. So you can remember like this. For example, you tell me one thing. If these are the people, and let's assume these are the set of syringes, syringe, or I can say injections. Okay. So tell me, if these are the syringe, or I can say what we call injections, right? Yes or no? So you can see this. Okay, if this is the set of people, and let's assume these are the syringes. Now, in this situation, what you can say, if you have two different people, A and B, if they are different people, then what should happen? They should get different injections. Yes or no? Yes or no? If you have two different people, if two people are different, then they should get different injections. They should get different injections. Okay, anyway, this is just an analogy. Okay, but I hope you understood this. So it is a coincidence, right, that they are calling it injective function, they are calling it injection, and also the same thing happens with the injections also. Okay, if you have two different people, they should get different injections. Yes or no? Is this clear? Please tell me. Let me know. So this is how also you can remember. Very simple point. Anyway, the point is simple. When can you say this function? You have a function. When can you say this function is injective? Or I can say this function is one-to-one. This function is one-to-one if and only if for every two different elements of the domain, their mapping also must be different. Remember, different elements should map to different elements. The idea is simple. Okay, in simple words, I can say, what are the simple words? In simple words, I can say different elements mapping to different elements. Yes or no? Different elements should map to different elements. Different elements must map to different elements. Must map to different elements. To different elements. Yes or no? Very simple. So different elements must map to different elements. This is the definition of injective function. If you have two different elements, their images also must be different. Okay, and this should happen for all A, B. Okay, for all A, B, this should happen that whenever they are different, their images also must be different. The same thing I can say like this. The same thing I can say for all elements, this should happen. If their images are same, then elements also must be same. Okay, so very simple. Now, what is the definition of surjective function? When can you say f is surjective? When can I say this f? This is a surjective. This is a surjective. When can I say this function is surjective? Another name is onto. Another name is onto. Another name is surjection. Another name is surjection. When can I say this function is surjective? This function will be surjective if and only if every element of codomain is covered. Okay, if and only if, remember, if and only if every element of codomain is covered. Every element of codomain, every element of codomain must be covered. Okay, is it covered? Is this clear? Is captured, or I can say covered. Is this clear? Please tell me. Every element of codomain must be covered. Then I can say that this function is surjective function. So very simple point. I can say that for all elements in the codomain, what I can say, if you take any element in the codomain, if you take any element in the codomain, what must happen? Please tell me. For every element in the codomain, what should happen? There should exist some element in the domain such that fx equal to y. Yes or no? Okay, for every element in the codomain, whatever element you take in the codomain, there must be some element of the domain which is mapping to y. Okay, is this clear? For every element of the codomain, there must be some element in the domain which is mapping to y. Or I can simply say that every element of codomain must be covered. Yes or no? So whatever element you take in the codomain, that must be covered. So this is the idea. When can I say f is surjective? The idea is simple. When can I say f is surjective? F is surjective if and only if in the codomain, this is your codomain. In the codomain, if I take any element, for example, this element I take, this must be covered. Means at least one element must map to it. Okay, remember, this is fine. Yes or no? In a function, is this allowed? In a function, is this allowed? Tell me, is this allowed? Yeah, this is fine. In a function, this is allowed. Yes or no? So this is allowed. For example, if you take this element also must be covered. This element also must be covered. Tell me, is this possible? Is this possible? Is this possible? No, this is not possible in a function, because this is a function. Remember, this is a function. Because it is a function, this is not possible. This is not possible. So the point is simple. Surjective means every element of codomain must be covered. Every element of codomain must be covered. Okay, so this is the idea of surjective function. Every element of codomain must be covered. I can say for every element of codomain, there should be some element, at least one element in the domain whose image is y. Okay, whose image is y. So this is the simple idea. This is the definition of surjective function. Now tell me, what is the definition of bijective function? When can I say f is bijective? When can I say f is bijective? Tell me. Bijective, another word, another name is bijection. Another name is bijection. Another name is one-to-one correspondence. One-to-one correspondence. One-to-one correspondence. These are the different names. So this is one word, remember. One-to-one correspondence. These are the different words. So tell me, when can I say a function is bijective? Function is bijective if and only if it is injective as well as surjective. Function is bijective if and only if f is injective also, and f is surjective also. F is injective as well as f is surjective. So this is the point. So remember, a function is bijective if and only if it is injective and it is surjective. If both the properties you have, then that will be called bijection. That will be called one-to-one correspondence. So these are the definitions. Okay, so we have seen all the definitions. You can easily notice what the definition of injection. The definition is very simple. For every two elements of the domain, what should happen? If images are same, elements must be same. Or I can say, if you have two different elements, then their images also must be different. And what the definition of surjection? Surjection is very simple. For every element of codomain, that must be covered. For every element of codomain, there must be some element in the domain such that fa equal to b. Okay, so you can see at least one element of domain maps to each element of codomain. This is the idea of surjection. Okay, let's move on now. Tell me, is this injective? Look at this and tell me, is this injective? Let me know. First of all, tell me, is this a function? First of all, you tell me, is this a function? Is this a function? Yes, this is a function. Now you tell me, is this one-to-one? Means, is this injective? Is this injective? Yes, this is injective. You can notice different elements have different images. Yes or no? Different elements have different images. You can just check it out. Different elements have different images. Okay, so this is injective also. Is this onto? Is this surjective? No, this is not surjective. Why? What the reason this is not surjective? This element is not covered. This element is not covered. Yes or no? This element does not have any pre-image. There is no element of domain which maps to earth. There is no element in this domain. There is no element in this domain which is mapping to earth. So this is not onto. What about bijection? Is this bijection? Because this is not onto, so this is not bijection. So this function is not bijection. Okay, so very simple. What about this function? What about this function? Tell me. This function. Is this a function first of all? Is this a function first of all? Yes, this is a function. You can check it out. You can check. This is a function. Every element of domain has exactly one image. Okay, every element is mapping to exactly one element. Every element is mapping to exactly one element. So now tell me, is this one-to-one? Is this one-to-one? This function is not one-to-one. For example, these two different elements have the same image. See, these two different elements, they are different elements, but they have the same image. But they have the same image. Okay, what about onto? Is this onto? Yes, this is onto. Every element of codomain is covered. Every element of codomain has at least one pre-image. For every element of codomain, there is at least one element in the domain which is mapping to it. Which is mapping to it. Okay. What about bijection? Is this bijection? Because it is not 1-1, so it is not bijection. Okay. What about this one? Tell me. What about this? Is this a function first of all? Is this a function first of all? Tell me. Yes, this is a function. You can say. What about one-to-one? Is this one-to-one? Is this one-to-one? Yes, this is one-to-one. You can see different elements have different images. So this is one-to-one. Is this onto? Is this onto? Yes, this is onto. Every element of codomain is covered. Yes or no? What about bijection? Is this bijection? Is this bijection? Yes, this is bijection also. Okay. So very simple. So I hope you understood all these things. What is surjective function? What is bijective function? Okay. All these things I hope you understood. Now let's see some important results. Let's see some important results. Okay. Some important results that we have already seen in our discrete mathematics course. Remember? So this is just a recap of some important results. We have seen these results in the function chapter in the discrete mathematics. Okay. So I will revise all of them. Every important result I will revise. So let's start with the first result. Tell me one thing. A simple question I'm asking. If there is bijection from A to B, what you can say about their cardinality? This is my first question. If let's assume you have a function, let's assume f is from A to B. If there exists bijection, I am asking if there exists bijection. If there exists bijection between, or I can say from A to B, or I can say between A comma B, if there exists a bijection, then what you can say about their cardinality? Then their cardinality will be same. Yes or no? Then this set A has the same cardinality as set B. This you already know. Very simple point. So if there exists a bijection, between A comma B or from A to B, then their cardinality will be same. Okay. Yes or no? Very simple point. So tell me, let me give you this set A. In this set A, you have 3 elements. Let me give you this set B. Okay. Now let me give you a function. Okay. Consider this function. Now I am giving you a function. Tell me, is this bijection? Is F bijection? Is F bijection? Is F bijection? Let me know. The answer is no. The answer is no. So can I say, if F is not bijection, can I say they have different cardinality? This function is not bijection. This function is not bijection. This function is not bijection. Does it imply they have different cardinality? Does it imply they have different cardinality? No. No. What is the problem? What is the problem? Tell me, where is the problem? Where is the problem? The problem is, remember, there exists a bijection. Is there exists a bijection? Yes or no? Remember this. There exists. This is important. There exists a bijection. Can you create a bijection? There exists a bijection. I'm not saying that every mapping is a bijection. Yes or no? We are not saying that every mapping should be bijection. Do you agree with me? We are not saying that every mapping should be bijection. We are simply saying there exists a bijection. There exists a bijection. So tell me, between these two sets, is there exist a bijection? Let me know. Is there any bijection between these two sets? Can you create a bijection between these two sets? Between these two sets, can you create a bijection? Please tell me. Can you create a bijection? Can you create a bijection? Yes, of course you can create a bijection. For example, you can create this bijection. So I can say bijection exists, right? Yes or no? This F2, this is bijection. So bijection exists. So can I say, so bijection exists? Agree with me? Bijection exists. This word, focus on this word, exists. Bijection exists. So because bijection exists, so what will happen? So I can say their cardinality will be same. Yes or no? Bijection exists, so their cardinality will be same. You can notice their cardinality is same. So this is the simple idea. You have set A, set B. If you have set A, set B, this is the simple idea. You have set A, set B, and if there exists a bijection between them, then I can say their cardinality will be same. Is this clear? Please tell me. Let me know. Is this clear? Now tell me one more thing. If their cardinality is same, let's assume you have set A, set B. Let's assume you have set A, set B. If their cardinality is same, then can you guarantee there is a bijection? Can you create a bijection? If their cardinality is same, there exists a bijection. Then there exists a bijection. Can you create a bijection? There exists a bijection. Tell me, from A to B. Can you create a bijection from A to B? Yes, of course. If their cardinality is same, they have same cardinality, then you can easily create a bijection. Yes or no? You have same cardinality. This set A, this set B, they have same cardinality. A1, A2, and so on. Okay, B1, B2, and so on. They have same cardinality, remember. Because they have same cardinality, so you can create a bijection. So you can create a bijection. So there exists a bijection. So finally, what I can say, tell me. This is the final result. If you have set A, set B, remember these can be any set. Please understand, these can be any set. These can be finite or they can be infinite. They can be finite, infinite, any set. Finite, infinite, countable, uncountable, whatever. Okay, these can be any set. This is what I'm saying. Whatever two set you take. So please tell me, when can I say they have same cardinality? Can I say if they have same cardinality, then there exists a bijection? Yes or no? If they have same cardinality, then there exists a bijection. Then there exists a bijection. Okay, between A, B. Between A, B. And if there exists a bijection, then what you can say? Then they have same cardinality. So this is the definition. This is a if and only if statement. Yes or no? I can say this is if and only if statement. Two directions. So I can say cardinality of A is equal to cardinality of B if and only if there exists a bijection between them. Okay, there exists. This is important. There exists. That you can create some bijection between them. There exists a bijection between them. Okay, very simple point. So this is the conclusion. So tell me, are you comfortable with this conclusion? Tell me. You have two sets. They can be finite or infinite. Remember, these two sets, they can be finite or they can be infinite. Set A, set S, T. So tell me, their cardinality will be same if and only if there exists a bijection between S, T. Yes or no? Very simple point. Now let me ask you another question. You have set A, set B. If there exists an injection, what you can say? If let's assume you have set A, set B. Okay, two things I'm asking. The first question, let's assume cardinality of A is less than equal to cardinality of B. Okay, remember they can be any set. Please understand, they can be any set. They can be finite, they can be infinite, they can be countable, uncountable, whatever. Okay, we will study what is countable, what is uncountable, we will study. But I am saying that they can be finite, infinite, whatever set you take. They can be any set. Now tell me, if cardinality of A is less than equal to cardinality of B, then what you can say? Tell me, if cardinality of A is less than equal to cardinality of B, can I say there exists a injection? Can I say you can create an injection? There exists an injective function. Can you create an injection from A to B? You can create an injection from A to B, right? Yes or no? Very simple. You can notice your set A, cardinality of A is less than cardinality of B. Yes or no? Remember, cardinality of A is less than cardinality of B. This is already given to you. So in this situation, what you can do? Cardinality of A is less than cardinality of B. In this situation, what you can do? You can create an injection. You can create injection, right? Yes or no? You can create injection. So like this, This is what I'm saying. You can create injection. There exists a injection. The same thing I can say, if there exists a injection, what you can say? Another question. If there, you have set A, set B, if there exists a injection, if there exists injection, or I can say injective function, if there exists an injective function from A to B, means from A to B, there exists an injective function, then what you can say about their cardinality? Then their cardinality will be what? What you can say about their cardinality? Tell me. What you can say about their cardinality? The answer will be that cardinality of A, that will be less than equal to cardinality of B. Yes or no? Agree with me? Okay, so very simple point. If there exists an injection, means this is your set A, this is your set A, this is your set B. Okay, so if there exists an injection, means you have an injection. Okay, there exists an injection. From set A to set B, there exists an injection. This type of injection you have. Okay, this type of injection you have. There can be extra element. There may or may not be extra element. There may or may not be extra element. Yes or no? In B, there may or may not be extra element. So I can say that cardinality of A will be less than equal to cardinality of B. Agree? So again, we have a if and only if statement. What I can say? So if you have set A comma set B, what I can say? Set A comma set B, I can say that cardinality of A will be less than equal to cardinality of B if and only if, when can I say this thing? I can say if and only if there exists an injection. There exists a injection. There exists an injection from A to B. There exists an injection from A to B. All these points, if you remember, we have already seen in the discrete mathematics. I am just revising. These are quite intuitive. Please tell me. These are intuitive points, yes or no? See, you can see if cardinality of A is less than equal to cardinality of B, then it simply means there exists an injection. You can create an injection. And if there exists an injection, then cardinality of A will be less than equal to cardinality of B. All these points are quite intuitive. Okay, if you think about it. So all these points, these are quite intuitive. So tell me, did you understand this point? Let me know. You have two set, S comma T. These are two set. They can be finite, they can be infinite, they can be whatever two set. Okay. I can say cardinality of set S, that is less than equal to cardinality of set T if and only if there exists an injection. There exists an injection from S to T. There exists an injection from S to T. Yes or no? Okay. Now tell me one thing. The same thing I can say in terms of surjection. When can you say that set S, cardinality of set S, that is greater than equal to cardinality of set T? When can you say this? Cardinality of set S, that is greater than equal to cardinality of set T. When can you say this? Cardinality of set S, that is greater than equal to cardinality of set T. When can you say this? This will happen if there exists a surjection. Yes or no? You can cover all of them. There exists a surjection. You can cover all of them. Yes or no? So in this situation, I can say this will happen. Remember, this will happen if and only if there exists a surjection. There exists a surjection from where to where? There exists a surjection from where to where? There exists a surjection from where to where? From S to T. There exists a surjection from S to T. Okay, so this is the point. You can see if you have two set S comma T, they can be finite, they can be infinite. When can I say set S cardinality is greater than equal to set T cardinality? That will happen if and only if there exists a surjection from S to T. There exists a surjection from S to T. Yes or no? There exists a surjection from S to T. Now tell me one thing. Let me know one thing. When can you say that set S cardinality is greater than equal to set T cardinality? Okay, this same thing I can say like this, that set T cardinality is less than equal to set S cardinality. Yes or no? These two things are basically same. Okay, set S cardinality, that is greater than equal to set T cardinality. I can also say like this. Now what I can say, remember these two things are same. Now what I can say, when this will happen, please tell me. When this will happen, set T cardinality is less than equal to set S cardinality. When this will happen? When this will happen? When there exists a injection. When there exists a injection. From where to where? From where to where? from T to S. From T to S. Yes or no? Yes or no? See, these two things are same. These two things are same. These are same. Exactly same. Yes or no? Set S cardinality is greater than equal to set T cardinality. That is same as set T cardinality less than equal to set S cardinality. These two things are same. So what I can say? I can say that there exists an injection from T to S. There exists an injection from T to S. Yes or no? Agree with me? Is this clear? Please tell me. Did you understand this? Yes or no? So, are you comfortable with this result? Please tell me. Let me know. Did you understand this? Set S comma T, they are two set. They can be any set. Now, when can I say that set T cardinality is less than equal to set S cardinality? When can I say if and only if there exists injection from T to S? Is this clear? Let me know. When can I say this will happen? When can I say this will happen? When there exists an injection from T to S. When there exists an injection from T to S. Is this clear? Let me know. Yes or no? Now let's move on. Now let's see this one. Tell me this point. Set S cardinality is less than equal to set T cardinality. The same statement can I write like this? The same statement can I say that set T cardinality is greater than equal to set S cardinality? Yes or no? These two things are same. The same thing. See what I'm doing. It's very simple. A is less than equal to B. Can I write it like this, that B is greater than equal to A? Are they same or not? These two things, are they same or not? They are same. This is what I'm doing. Yes or no? So this is what I'm saying, that these two things are same. Now tell me, what I can, when can I say this? Remember, these are same. So when can I say this? When can I say this? When there exists a surjection from where to where? When there exists a surjection from where to where? From T to S. Yes or no? From T to S. From T to S. When there exists a surjection from T to S. Is this clear? So this is the point you can notice. Set S cardinality is less than equal to set T cardinality if and only if there exists a surjection from T to S. There exists a surjection from T to S. Okay. I can also say there exists an injection from where to where. I can also say there exists an injection from where to where. I can also say there exists an injection from where to where. Tell me. The same thing I can also say there exists an injection from S to T. Okay. So very simple. Yes or no? I hope all these points are clear. So finally, this is a simple point. You tell me one thing. If S cardinality is less than equal to T cardinality and T cardinality is less than equal to S cardinality, what you can say now? If this also happens, this also happens. If this also happens, this also happens. Then what you can say? Please tell me. If this also happens, this also happens. If and only if this will happen, if and only if set S cardinality is equal to set T cardinality. Yes or no? Yes or no? You can notice set S cardinality that is less than equal to T cardinality, and this T cardinality that is less than equal to S cardinality. So that will happen if and only if they have same cardinality. Yes or no? Very simple. Okay. So very simple point. This is quite simple, right? For example, if A is less than equal to B and B is less than equal to A, what you can say about them? A is less than equal to B, B is less than equal to A. When it will happen? When it will happen? It will happen if and only if A is equal to B. When this will happen? This will happen if and only if A is equal to B. The same thing I'm doing here. Yes or no? So please tell me, is this clear? Is this clear? Okay. All these points, these are quite intuitive. All these definitions, these are quite intuitive. I hope you understood. Okay. Yes or no? Is there any confusion? Please let me know. Everything is quite intuitive if you think about it. Quite simple. Is there any confusion? I'm telling you all the points one by one. Every point I'm telling you one by one. Now tell me, if you want to prove this, then what you will do? If you want to prove this, what you will do? Please tell me. If you want to prove that set S cardinality is less than equal to set T cardinality, what you will do? You can create an injection from S to T. Yes or no? What you can do? You can create an injection from S to T. So this is your method number one. Method number one, what is that? Create an injection from S to T. Show Create an injection from S to T. Agree with me? Create a injection, a injective function from S to T. Agree? Create an injective function from S to T. Yes or no? If I can create injective function from S to T, can I say this? Tell me, let me know. If I can create injective function, I can create injective function from S to T. Can I say this? Yes, of course. Yes or no? So this is what I'm saying. Method number 1. What is method number 2? What else you can do? What is method number 2? What is method number 2? Please tell me. Method number 2 is create a surjection from T to S. Create a surjective function from T to S. Create a surjective function from T to S. Yes or no? From T to S. Create a surjective function from T to S. Is this clear? Okay, let me know. So actually, this is what we will do. This is the most popular. This is what we will apply. Okay, we will apply this method. We will apply this method. But let me tell you, in the true false, they can ask you this also. Yes or no? In the true false, in some MSQ question, in the true false, they can ask you this also. Is this clear? Let me know. Please tell me, when can you say that set S cardinality is less than equal to set T cardinality? When can you say? If you want to say this, if you want to prove this, then create a surjective function from T to S. Create a surjective function from T to S. Because surjective function from T to S, what that will mean? Let me know. What that will mean? Please tell me. What that will mean? If you have a surjective function from T to S, what that will mean? That will mean T cardinality is greater than equal to S cardinality. And that is the same thing here. And that is the same thing here. This and this, they are same, yes or no? This and this, they are basically same. Please tell me, did you understand this? Is this clear? This and this, they are basically same. They are same equations. This equation, they are same equation. Okay, let's move on. Tell me about this one. If you want to prove this, then what you will do? Let me know. If you want to prove this, then what you will do? What we will do if we want to prove this? What method we will apply? We can give an injection from T to S. Yes or no? Create an injection from T to S. Create an injection from T to S. From T to S. Yes or no? From T to S, you create an injection. If you can create an injection from T to S, that's fine. This is the method we will use. See, can you notice injection is actually easier? This is what we will use. Okay? Because injection is always actually easier. Let me tell you. If you want to find injective function, that is easier than finding surjective function. Whenever you want to find injective function, that is easier than finding a surjective function. So this is the reason. So you can see, if you want to prove this, then you can create an injection from T to S. What is another way? Let me know. What is another way? Just in case if they ask you in the true false, what is the another way? I can also do that. I can create a surjective function from S to T. Yes or no? I can create a surjective function. I can create a onto function from S to T. I can create a onto function from S to T. Is this clear? Let me know. I can create a onto function from S to T. Because remember, if I create a onto function from S to T, what that means? If there exists onto function from S to T, what that means? Please tell me. If there exists onto function from S to T, that means S cardinality is greater than equal to T cardinality. Okay, you can say this. So very simple. All these points, are you comfortable? Please tell me. Let me know. Are you comfortable with all these points? Now, finally, how can you prove this? If I want to prove that S cardinality is equal to T cardinality, what are the different ways? What is the method one? What is the method one? Method one is create a bijection. Yes or no? Method one is create a bijection. If you want to prove that, then that they have same cardinality, then the method one is create a bijection. Create a bijection between S comma T. Between S comma T. Just create a bijection. Agree with me? Just create a bijection. If you want to say that they have same cardinality, then create a bijection. Bijection between S comma T. What is the method number 2? What else you can do? If you don't want to create a bijection, then what you can do? If you don't want to create a bijection, then what you can do? Then what you can do? Then you can do like this. Then you can say, first you prove this, also you prove this. Yes or no? First you prove this, also you prove this. Agree with me? Do you agree with me that first you prove this, also you prove this? Both of them you prove. Both of them you prove. Okay. You prove that this also happens as cardinality is less than equal to T cardinality, and T cardinality is less than equal to S cardinality. So both of them you prove. Now tell me, if you want to prove this, what you will do? If you want to prove this, what you will do? You will create injective function. You will create injection from S to T. And if you want to prove this, what you will do? If you want to prove this, what you will do? You will create injection from T to S. Yes or no? So both of them you do. You create injection from S to T. You create injection from T to S. This is your method number 2. Is this clear? Please tell me. Let me know. This is your method number 2. If you want to prove two set, they have same cardinality, then what you can do? See, the idea is simple. If you want to prove A is equal to B, then you can just prove that A is less than equal to B, and you can prove that B is less than equal to A. These two things you can prove. Agree with me? Yes or no? If you want to prove this happens, then you can just simply do this also you do, this also you do. So this is what I'm saying. If you want to prove they have same cardinality, then you can prove that this will also be true, this also will be true. Okay. So if you want to prove that S cardinality is less than equal to T cardinality, then create an injection from S to T. And if you want to prove this, then create an injection from T to S. What is method number 3? What is method number 3? Please tell me. What is method number 3? The method number is 3 is like this. You can create injection as well as surjection from S to T. Yes or no? Again, the same thing. What you do this also, and you do this also. Both of them you do. Okay, both of them you do. Now remember, if you want to do this, then what you can do? You can create an injection from S to T. You can create an injection from S to T. And if you want to do this, then you can create a surjection from S to T. Yes or no? You can create a surjection from S to T. So you can create injection from S to T. You can also create surjection from S to T. So this is how also you can prove. Is this clear? All these points, please tell me. All these points, are they clear? Let me know. Let me know. What is method number 4? What is method number 4? The method number 4 is like this, that you do this, that T cardinality is less than equal to S cardinality, and T cardinality is greater than equal to S cardinality. So for this, what you will do? For this, what you will do? Please tell me. If you want to do this, then what you will do? You will create injection from where to where? You will create injection from where to where? From T to S. And if you want to do this, then you will create injection from where to where? Then you will create injection from S to T. So anyway, I hope you understood all these points. Okay, so like this you can do. Are you comfortable? Please tell me. Like this you can do all these things. So did you understand so far whatever we have seen? Did you understand? Please tell me. So far everything we have seen, did you understand? Let me know. Is there any doubt in this? All these things are intuitive. So far everything we have seen, that is intuitive. Yes or no? So far everything was intuitive. Intuition was going on so far. Okay. Please tell me, will you forget any of these results? All these results. You can just think about it. Okay. If you want, you can just think about it. For example, if I randomly ask you, prove this, then immediately what will come to your mind? If I ask you this, then what will come to your mind? You want to prove that this set A cardinality is less than equal to set B cardinality, then create an injection. Yes or no? That will come to your mind. Agree with me? That will come to your mind, that create an injection. Just create an injection. Okay. If and only if there exists an injection, from A to B, just create an injection from A to B. Yes or no? Is this clear? Please tell me. So I'm saying that all these things are very intuitive. So if you have any confusion, you can just think like this. Okay, you can just think like this. Immediately you will see what to do immediately. Okay, so all these things, these are quite easy. Okay, let's move on now. Now, let me ask you one question. Let me ask you one question now. This is the question. Let's assume you have set A, set B. Let's assume you have set A, set B. Okay. And I'm saying that there exists an injection from A to B. There exists an injection from A to B. There exists an injection from A to B. But there is no, okay, there exists an injection from A to B, but there is no surjection from A to B. Okay, but there is no surjection from A to B. From A to B. In this situation, what you can say? There is an injection from A to B, but there is no surjection from A to B. There is no surjection from A to B. In this situation, what you can say? In this situation, what you can say about their cardinality? What you can say about their cardinality? Please tell me. Yes, very good, very good. In this situation, I can say that set A cardinality that is strictly less than set B cardinality. Yes or no? Agree with me? Yes or no? See, there exists an injection. What that will tell you? There exists an injection. What this will tell you? There exists an injection. What this tells you? What this tells you? This tells you that set A cardinality is less than equal to set B cardinality. Okay. But remember, there is no surjection from A to B. There is no surjection from A to B. Then it simply means that they cannot have equal cardinality. Yes or no? See, there is no surjection from A to B. What it simply means? Please tell me. Very simple question I'm asking. There is no surjection from A to B. What that means? That means they cannot have same cardinality. Yes or no? They cannot have equal cardinality. Agree? They cannot have equal cardinality. If there is no surjection from A to B, then they cannot have equal cardinality. So finally, from this and from this is what you got. Yes or no? If you combine these two, then this is what you will get. Is this understood? Please tell me. Is this understood? So tell me. So finally, this is what I'm saying, that set S cardinality is less than set T cardinality. Okay. Set S cardinality that is less than, strictly less than T cardinality if and only if there exists an injection from S to T. There exists an injection from S to T, but there is no surjection from S to T. But there is no surjection from S to T. Is this clear? This was the last point. This was the last point. Did you understand this? Please tell me. Because please notice that if there exists an injection from A to B, that means set A cardinality that is less than equal to set B cardinality. But there is no surjection from A to B. There is no surjection from A to B means they cannot have same cardinality. They cannot have same cardinality. So finally, I can say that if you combine these two, this, if you combine these two, you will get this. Is this clear? Please tell me. So these are all the points that we have seen. I hope you are comfortable so far. So far, whatever we have seen, are you comfortable with it? Did you understand all these points? These are very important points. We will use them again and again. So tell me, let me know. Did you understand everything? Did you understand everything? Please tell me. Let me know. So far, everything did you understand? Is there any confusion? Is there any confusion, any doubt? Let me know. All these points are quite intuitive. You can use the intuition. All these points, they are very intuitive points. You can just use your intuition and you can understand them. You can understand and also you can remember. Okay. So very intuitive points. Now let's move on. Now let's see our chapter number 1, that is countability. So far, we did not see the countability. Yes or no? So far, we have just seen all these things. So far, what we have done? So far, we have just done the revision of functions. Yes or no? We have done the revision of function. What is function? What is injection? What is surjection? What is bijection? So far, these things we have done. So far, this is what we have done. And all these things we have already done in discrete mathematics. Okay, we have already done all these things. Already done in functions. When we studied functions in discrete mathematics. Okay. So now we will start the chapter. The chapter will start now. So far, whatever we have seen, that was prerequisite, but I have covered it. Every prerequisite that is required, I have covered. Let me know. Comfortable, right? Yes or no? All the prerequisite I have covered. Now let's see the chapter. Now let's see the actual chapter, that is countability. So let's see chapter number 1, that is motivation. What the motivation to study this chapter? What is this chapter about? That is the question. Yes or no? In this chapter, what we study? What is this chapter about? So let's see this. What this chapter is all about. Let me tell you. This chapter is all about understanding infinity. This chapter, if someone asks you countability, uncountability, countable set, uncountable set, this chapter is all about understanding infinity. In this chapter, you will understand infinity. You will actually understand what is this infinity, what are the different levels of infinity. Okay. So everything you will understand in this chapter. So basically, this chapter is all about understanding infinity. Okay. So focus. This is very interesting chapter, let me tell you. So do you really understand infinity? Can you say that you understand infinity? What is this infinity? What is this infinity? Do you really understand infinity? Do you really understand this infinity? So let me tell you, if you don't, then in this chapter you will understand. Okay, so just wait. This is a very interesting chapter. So first of all, before we start, I want to tell you a few basic things that you already know. Infinity is not a real number, right? Yes or no? Infinity is not a real number. It is not a complex number also. In this chapter, you will understand infinity. Okay, in this chapter, you will really understand infinity, the concept of infinity. So remember, infinity is not a real number. Infinity is not a complex number. Okay, so infinity, for example, this infinity, remember, this does not belong to the set of real numbers. Okay, similarly, this infinity does not belong to the set of complex numbers. Okay, so these, for example, this infinity does not belong to the set of integers. This infinity does not belong to set of natural numbers. Simple point, I am saying that infinity is not a real number. Infinity is not a real number. So tell me one thing. So for example, what some students think, let me tell you what some people think. Some people think like this, that some people think that real numbers are like this. Real numbers, they think like this, that this is the real line. This is 0 here. This is 1 here. And if you go like this, at some time you will reach infinity. Yes or no? And if you go like this, at some time you will reach minus infinity. Yes or no? This is what people think. This is what people think. But remember, this actually means that you can never end. This does not mean that this is some point. Remember, this is not some point. Is this clear? This is not some point. This is not some end point. Okay, if you are thinking that, okay, this is the end point. This is the end point. No, actually what this means, this means that this sequence will never end. What this means, please tell me. This is not some end point, remember. So whenever you write like this, in your childhood also you have done this. See, whenever you do like this, for example, this is the real line. This is 0, this is 1, this is 2. Okay, we write like this. Agree? Sometimes we do like this. Yes or no? Have you seen this? This is the real line. This is your real line. Now on the real line, remember, when we write like this does not mean that this is some end point. What some people think that, okay, this is the last point. This is the last point, like final destination. Yes or no? This is not a final destination. Actually, what this means that this sequence will never end. Okay, this means that this sequence will never end. Is this clear? This means that this sequence will never end. This is what it means. This sequence will never end. Will never end. Is this point clear? What this means? That this point, this actually, if you are thinking that this is the final point, if you are thinking that this is some final destination, this is some last point, or I can say end point, actually what this means, this means that there is no last point. Yes or no? Actually, this means that there is no last point. There is no largest real number. Yes or no? There is no largest real number. Is this point clear? Actually, this means, this symbol actually means that there is no largest real number. because this sequence will never end. This sequence will never end. So there is no largest real number. Is this clear? Please tell me. Did you understand that infinity is not a real number? Infinity does not belong to your set of real number. So infinity is never a real number. Yes or no? So when you write the set of natural numbers, this is your set of natural number 1, 2, 3, and so on. Will you ever get this? Will you ever get this? Please tell me. Will you get this? No, you will never get this. You will never get this. So please understand that this is not a number. Please understand this is not a number. This thing does not belong to set of natural number, because this is not a real number. This is not a real number. Okay, this is not a real number. So what this actually means, if I write like this, if I write, then what it means? It means that there is no largest natural number. Yes or no? This simply means there is no largest natural number. Okay, so when I say that, when I write like this, you can see here, when I write like this, it simply means this sequence will never end. Similarly, this sequence will never end, means there is no largest natural number. There is no largest natural number. There is no largest natural number. Okay, because this sequence will never end. So there is no largest natural number. Very simple point. Okay, so I hope you understood. Now, so read this. Let me connect my laptop to charger. So now let's see this. Intuition does not work with infinity. Okay, I will prove it to you. Don't worry. We will prove it to you that intuition does not work. Intuition does not work with infinity or infinite set. Okay, infinite sets, they behave in a weird way. Okay, so if you want to handle infinity, then what you need to do? If you want to handle infinite set infinity, then what you need to do? You need to apply the mathematical definitions. Don't apply the intuition. Apply the mathematical definitions. Is this clear? Please tell me, is this clear? So remember, intuition does not work with infinity or infinite set. I will prove it to you. Okay, we will prove it. We will prove it. So just apply the mathematical concepts. Just apply the mathematical definitions. Now let's see. So remember, don't treat infinity as a real number. This is what most students do. This is the mistake. Don't treat infinity as an end point. Is this clear? Please tell me. Don't treat infinity as some end point. Infinity actually means there is no end point. Yes or no? So don't treat infinity as some end point, that there is some end point. There is this end point. Okay, there is this end point. No, infinity simply means there is no end point. Is this clear? So don't treat infinity as a real number. Don't treat infinity as some end point. Okay, so now let's see. In fact, actually, let me tell you, when a sequence is infinite, then what it means? When a sequence is infinite, what that actually means? That actually means there is no end point. Yes or no? That actually means there is no end point. When a sequence is infinite, it simply means there is no end point. Now let's see this question. Tell me the answer for this question. Is there a smallest natural number? Is there a smallest natural number? The answer is yes. Okay, the answer is yes. What is the smallest natural number? That is 1. So yes, there is a smallest natural number. Now tell me the answer for this question. Is there a largest natural number? Is there a largest natural number? Do we have a largest natural number? The answer is no. How can you prove it? How can you prove it? Let's see the proof. What is the proof? If you say, assume there is a largest natural number. Okay, assume n is the largest natural number. Assume n is largest natural number. Okay, let's assume that n is largest natural number. Then what you can do? Then what is n plus 1? Yes or no? Then n plus 1. The n plus 1 also belongs to set of natural number. And you can notice n plus 1, that is bigger than n. So this is the contradiction. Is this clear? Please tell me. Yes or no? Very simple. If you assume that n is largest natural number, then I can say that n plus 1 that is greater than n. Now some people will think, sir, but what about infinity? But what about infinity? Infinity plus 1 is also infinity. Infinity plus 1 is also infinity. So this is the largest number. This is the largest natural number. So tell me, what is the mistake here? What is the mistake in this logic? In this logic, what is the mistake? This is not even a natural number, first of all. First of all, this is not even a natural number. Infinity is not even a natural number, first of all. Yes or no? This infinity does not belong to your set of natural number. Your set of natural number is like this. N equal to 1, 2, 3, 4, and so on. And so on. You don't have infinity here. You don't have infinity here. Is this clear? This is the set of natural number. There is no infinity in this set. In this set, there is no infinity. So don't consider infinity as some endpoint. Is this clear? This is what I'm saying again and again. Don't consider infinity as some endpoint. There is an endpoint. No, there is no endpoint. So remember, this is wrong. This is wrong. Okay. So very simple, because infinity is not a natural number. So this is the idea. Now let's see this. Tell me the answer for this question. Read this. Assume H is a hotel. Assume H is a hotel with infinite number of rooms. With infinite number of rooms. There are infinite number of rooms. Assume first room is room number 1. Is there a last room in this hotel? Is there a last room? The answer is no. There is no last room. Yes or no? Because you have infinite number of rooms. The first room is room number 1. Okay, this is your room number 1. Then this is your room number 2. This is your room number 3. So like this you have. This is an infinite hotel. So there is no last room. Yes or no? If there is a last room, then what will happen? If you assume this is the last room, then this is finite number of rooms. Yes or no? If you assume this is the last room, then this is a finite number of rooms. Now you have finite number of rooms. Is there any room numbered this? Tell me, is there any such room? Is there any such room? No, there is no such room. Okay, this is what I'm saying. There is no such room. There is no such room. This is what I'm saying again and again, that don't consider this infinity as some endpoint. Okay, so there is no such room. I hope you understood. So actually, basically we can just say that you have infinite number of rooms. Means your number of rooms is not finite. Okay, your number of rooms, that is not finite. So this type of hotel you have. This is your hotel H. Okay, so I hope you understood so far whatever we have seen. Now let me prove that infinite set, they behave in a weird way. Means intuition does not work with infinite set. See, intuition will work with finite set. Your intuition will always work with finite set. Whenever you are dealing with finite set, your intuition will work. But your intuition will not work with infinite set. Let me prove it to you. Okay, infinity, or I can say infinite set, they behave in a weird way. Let's see one very famous example. And that famous example is Hilbert's Grand Hotel. This is a very famous example. Let me tell you actually what happened. This Hilbert, this was a mathematician. This Hilbert, he was a mathematician. This Hilbert, he was a mathematician. Now, at that point of time, almost I can say in 1900s, so this Hilbert was a great mathematician in 1900s. What actually at that point of time, people, some mathematicians, they used to think that they have understood infinity. Okay, some mathematicians, this is what they used to think, that they have understood infinity. Okay, then this Hilbert created one paradox, or I can say Hilbert created one game, or I can say this scenario. Hilbert created this scenario. So this scenario will tell you that you cannot apply intuition with infinity. You cannot apply intuition with infinity. Okay, so this is what Hilbert did. Hilbert created this scenario. In this scenario, you will see that your intuition does not work with infinity. Okay, and there was another person, Cantor. He did something bigger than Hilbert. Okay, I will discuss it. Okay, he also did something in the 1900s. He created infinite levels of infinity. What he proved? He proved that some infinity are bigger than other infinity. Okay, what he proved? He proved that some infinity are bigger than other infinity. Some infinity are bigger than other infinity, are bigger than other infinity. Okay, anyway, don't worry, we will prove it to you. Okay, so by the end of this countability, you will become expert in this. Anyway, we will prove it. This also we will prove. But let's come to Hilbert. So let's see this Hilbert's Grand Hotel. So why I am giving you this example, Hilbert Grand Hotel? Because I want to prove that in finite set, they behave in a weird way. So your intuition will work with finite set, but your intuition will not work with infinite set. Okay, so let's see this example, Hilbert Grand Hotel. So first of all, you tell me the answer for this question. Tell me the answer for this question. Assume H is a hotel with finite number of rooms. You have finite number of rooms. Okay, maybe 100 rooms, 200 rooms. But the point is you have finite number of rooms. Okay, now, can you accommodate a new guest if every room is already occupied? Tell me. If every room, I am saying every room, remember, I am saying every room is already occupied. Can you accommodate a new guest? The answer is no. Yes or no? The answer is no, because you have finite number of rooms. This is quite intuitive. Your intuition is working or not? Tell me. For example, this is your hotel. In this hotel, you have room number 1, room number 2, and so on. Let's assume room number 100. Let's assume you have 100 rooms. Okay, now you can notice if this is already occupied. Okay, this room occupied, all the rooms are occupied. This room is occupied. This is also occupied. This is also occupied. Every room is occupied. You can notice. Now, if a new guest comes, okay, if a new guest comes to this hotel, this is a new person. Can he get a room? Can this new guest get a room? The answer is no. Yes or no? There is no room available. Agree with me? So this is a finite hotel. So your intuition is working because every room is already occupied. So new guest cannot come. Okay, I can say we cannot accommodate. Okay, so this is the simple point. We cannot accommodate. Now tell me, the same scenario, if I give you an infinite number of rooms, if I give you a hotel with infinite number of rooms, you have a hotel with infinite number of rooms. Let's assume, this is interesting, every room is filled. I am saying every room is already occupied. Can you accommodate a new guest? Please tell me. What do you think? Remember, every room is filled. Every room is already occupied. You have an infinite number of rooms. In this hotel, you have infinite number of rooms. Now, every room is already occupied. Now, can you accommodate a guest? Tell me. Can you accommodate a new guest? A new guest is coming. Can you accommodate? What do you think? And the answer is yes. And the answer is yes, you can accommodate. How will you accommodate? Please tell me. The answer is yes, you can accommodate. Remember, every room is already filled. You might be thinking, sir, every room is already filled. So can you, okay, no, you cannot create a new room. Can you create a new room? If you can create a new room, you can create here also. Of course, you cannot create a new room. If a new guest will come, will you create a new room? If you create a new room, that will take maybe 100 days. Okay, maybe 20 days. Yes or no? Will the guest wait? You cannot create a new room. See, if you can create a new room, that you can create also here also. In this hotel also you can create in new room. So don't create new room. Don't create new room. Okay. Yes or no? This is what I'm saying. You have an infinite number of rooms you have in this hotel. Okay. But remember, every room is filled. Every room is filled. Then can you accommodate a new guest? The answer is yes. So what you will do? This is your hotel. This is infinite hotel. Remember, this is infinite hotel. You can see. This is the hotel. Okay. Now in this hotel, can you accommodate a new guest? Every room is filled. This room filled. Every room is filled. So tell me what to do. What you will do if you want to accommodate? Very simple point. Tell me, if you have an infinite hotel, is there a last room? Is there a last room? Simple question I'm asking. Is there a last room? Is there a last room? Can you say that there is a last room? That this is the last room? Is there a last room? The answer is no. Yes or no? The answer is no. Remember infinity. For example, is there this type of room? Do you have? Do you have this type of room? No, there is no such room. Okay. So this is what I'm saying. There is no last room. Now what you can do? Already every room is filled. Okay. In this hotel, what is happening? See, in this hotel, Let's assume these are the rooms. Room number 1, room number 2, room number 3, room number 4, okay, and so on. These are the rooms. Okay, these are the infinite number of rooms. Now every room has someone. Every room has someone. Every room that has someone. Already there is someone here. Okay, occupied. Every room is occupied. Now a new guest is coming. Now this new guest is coming. Okay, to this hotel. New guest is coming. So what you will do? How can you accommodate? This new guest is coming. Then how can you accommodate? This new guest has come. But every room is filled. Every room is filled. So what you can do? Very simple. Very simple. What you can do? See, you can say that, see, shift here. This person will shift here. This person will shift here. This person will shift here. Are you getting my point? This person will shift here. This person will shift here. If you do like this, then what will happen? Then what will happen? See, the person who is in the nth room, he will shift where? For example, there is a person in the nth room. He will shift to n plus 1th room. Yes or no? He will shift to n plus 1th room. He will shift to n plus 1th room. So can I say the person who is in the last room, can I say he is thrown out? The person who is in the last room, what about him? What about that person? What about that person? Because remember, every room is filled. Every room is already filled. So what about that person who is in the last room? What about that person who is in the last room? What about that person? Tell me, what about that person who is in the last room? Arey, there is no last room. Yes or no? There is no last room. This is what I'm saying. There is no last room. Yes or no? There is no last room. So very simple point that what you will do, this person will shift here. This person will shift here. And finally, what will happen? This room will be empty and this person will go here. Yes or no? So can you notice even the, so can you notice you have infinite hotel, this H, this is an infinite hotel. This has an infinite hotel, but still you can notice already full. This hotel is full, but still you can accommodate a new guest. Hotel full. Hotel is already full, but still you can accommodate. Yes or no? Still we can accommodate a new guest. A new guest we can accommodate. Please tell me, did you understand? Did you understand? Please tell me. A new guest we can still accommodate. Okay, we can accommodate. Because the beauty is this, that there is no last room. You might be thinking, sir, what about the last room? In the last room, this person will be thrown out. This person will be evicted. The point is, there is no last room. There is no last room. Yes or no? So all the people, can you say there is no person who is evicted? Yes or no? There is no person who is evicted. Is this clear? Please tell me. So this is the idea. So you can see that hotel is full, but still you can accommodate a new guest. So this is the idea. Very simple. You can see this is the Hilbert's Grand Hotel. This is an infinite hotel. A new guest is coming. This new guest is coming. So what this manager will do? He will shift. Okay. Then you can accommodate this new guest. So this is the idea. I hope you understood. So very simple. This is the point. Okay. This guest will go to the room number 2. This guest will go to room number 3. This guest will go to room number 4, and so on. So finally, you can accommodate the new guest. Okay. Yes or no? So this is what you can do. I hope you understood. Is this clear? So this guest, there is a guest here. To that guest, what you can say? You can say go to n plus 1. Yes or no? This guest is there. To this guest, you can say go to n plus 1. Go to n plus 1. So like this. So finally, the new guest you can accommodate. I hope you understood this. Please tell me. Yes or no? So can you notice? We can always accommodate a new guest in this hotel. We can always accommodate a new guest in this hotel, even if all the rooms are full. Is this clear? In this hotel, if all the rooms are full, then also we can always accommodate a new guest. A new guest we can always accommodate. Okay. So this is what I'm saying, that infinity does not work as per your intuition. Your intuition will not work with infinity. Infinity works in a weird way. Okay. So for infinity, you have to apply the mathematical concepts. Is this clear? Tell me the answer for this question. Let me know. Let me know the answer for this question. H is a hotel with finite number of rooms. Can you accommodate 100 new guests if every room is already filled? Every room is occupied. Can you accommodate 100 new guests? The answer is no. The answer is no. You cannot accommodate. Yes or no? Very simple. Okay. What about this question? In this Hilbert Grand Hotel, this is the Hilbert Grand Hotel with infinite number of rooms. How will you accommodate 100 new guests are coming? Remember, every room is already filled. Remember, every room is occupied. Every room is already occupied. Then how will you accommodate 100 new guests? What you will do? Very simple. Very simple. This person, whatever person you have, this is your hotel. In this hotel, you have room number 1, room number 2, room number 3, and so on. Room number n. Okay. So what you will do? Every guest will basically go to n plus 100th. Yes or no? So for example, this will go to 101. This will go to 101. This will go to n plus 100. So finally, what will happen? The initial 100 rooms will be empty. Yes or no? The initial 100 rooms will be empty. If you do like this, then initial 100 rooms will be empty. And now you can accommodate 100 guests. Okay. New 100 guests you can accommodate. Is this clear? Please tell me. New 100 guests you can accommodate. New 100 guests. Now you can accommodate them. Okay. You can put them in the first 100 rooms. Okay. You can put them in the first 100 rooms. Okay. Is this clear? Tell me one more thing. If you do like this, that 1 is going to 101, 2 is going to 102, n is going to n plus 100. If you do like this, is there any person who will be thrown out? Is there any person who will be thrown out? Is there any person who will be thrown out? No person will be thrown out. Yes or no? Every person will go to plus 100. Every person will go to plus 100. Every person will go to plus 100. What about the person in the last room? What about the person who is in the last room? What about that? What about that person who is in the last room? What about that person? There is no last room. Yes or no? Because this is infinite hotel. So there is no last room. Okay. So very simple. So you can accommodate 100 new guests. This is a question from Kenneth Rosen. Tell me the answer. Kenneth Rosen, question number 5. Show that, prove that finite number of guests arriving at Hilbert fully occupied hotel. Okay, finite number of guests arriving at Hilbert's fully occupied Grand Hotel can be given rooms without evicting any current guest. Without throwing out any current guest, finite number of guests you can accommodate. Can you do that? How will you do that? Tell me. Very simple point. Okay, so for example, if let's assume if n guests are coming, if n guests, or maybe I can say if k guests are coming, if k new guests are coming, remember k is a finite number. If k new guests are coming, okay, this k, this is a finite number, right? Yes or no? This is some natural number, maybe 100, maybe 200, maybe 1000, maybe 1 trillion. This k can be 1 billion trillion. Yes or no? This can be, this k can be very big. So this is a finite number, I can say. Remember, this is finite. Okay, so means this belongs to set of natural number. So what you will do? Can you accommodate? How to accommodate? Tell me. How to accommodate them? Let me know. How to accommodate these new people? We want to accommodate these new people. Let me know. How to do that? Very simple. Every person will go to which room? Every person will go to plus kth room. Yes or no? Okay, if some person is in the nth room, that person will go to n plus kth room. N plus kth room. Okay, just do the plus k. So finally, these k guests you can put in the first k rooms. Yes or no? Put in first k rooms. First k rooms. Okay, and remember, every guest will go to, I can say every old guest that will go to plus kth room. So like this. Is this clear? Please tell me. So you can notice that finite number of guests you can always accommodate in this hotel. I hope you understood. So this is the final point, that in a Hilbert Grand Hotel, remember, there is always room for one more. There is always room for one more. You can always accommodate one more person. Okay, yes or no? It's like India's private or government buses. Okay, the conductor will say there is always room. Yes or no? बहुत जगह है, बस full है, फिर भी बहुत जगह है. There is always room. Yes or no? Is this clear? Please tell me. Let me know. Rohit is asking, why are we not putting them from n plus 1th room? Because all the rooms are already occupied. See, Rohit is saying that these, so for example, this is room number 1, room number 2, room number 3. Okay. And this is room number n and so on. Now, if some k guests are coming, if some k new guests are coming, can you put them from the kth room directly? If k new guests are coming, can you put them directly in the kth room? Can you put them? For example, if let's assume 100 new guests are coming, can you start putting them from the 100 number? No, in the 100 already there is someone. In this room already there is someone. There is already someone. In every room there is someone. In every room you have someone. Every room has someone. Every room has someone. Now new people are coming. So what to do? Can you put them here? There is already someone here. Yes or no? Is this clear? See, Rohit is asking that, can you directly put from the 101 or maybe from the 100th, this new person, can you put directly from here? No, every room is occupied. Please understand, every room is occupied, fully occupied hotel. This hotel is fully occupied. Every room is occupied. So what to do? If you want to put this 100 guests, what to do? Shift, yes or no? Shift everyone to the plus 100 room. This person will go to 200. This person will go to 101, 103. This person will go to 101. Like this. Is this understood? Please tell me. Let me know. Is this clear? This Hilbert Grand Hotel, is this clear? Please tell me. Is this understood? Prashant is saying, if every room is occupied, then we can't shift anyone because every room is occupied. You are applying the intuition. Prashant, there is no last room. There is no last room. Okay, see, if I do like this, no person will be thrown out. Notice. Okay, Prashant, in this hotel, every room is filled. I agree. I agree with you. Every room is filled. Okay, I agree with you. Every room is filled. Give me one person who is thrown out. If I do like this, please tell me. If I do like this, then give me one person who is thrown out. Give me. Give me one person who is thrown out. Give one person who is thrown out. Who is thrown out? Give me one person who is thrown out. If I do like this, give one person who is thrown out. See, the same thing if I ask you in a finite hotel. Let's assume you have a finite hotel. Let's assume you have a finite hotel. In a finite hotel, if I ask you the same thing, okay, in the finite hotel, if I do the same thing, tell me which person will be thrown out. In a finite hotel, if I do the same thing, this is your finite hotel. In a finite hotel, if I do the same thing, one person will be thrown out. Yes or no? Give me one person who is thrown out. I can say this person number 3rd, this person P100. Yes or no? This person will be thrown out. Now tell me. Now I'm simple question I'm asking. In this infinite hotel, give me one person who is thrown out. In this infinite hotel, give me one person. Please give me one person who will be thrown out. Give me one person. If I do like this, give me one person who will be thrown out. The answer is no one. The answer is no one. Because every person will go to the next room. Every person is going to the next room. Every person will go to the next room. So no person is thrown out. Yes or no? Is this clear? No person is thrown out. Also, this room will become empty. Also, this room number 1 becomes empty. Yes or no? So no person will be thrown out. Also, room number 1 becomes empty. Room 1 becomes empty. A simple question I want you to answer. If you are thinking that, see, already full, I agree. Every room is occupied. Every room is full. But if I do this, give me one person who is thrown out. Can you give me? Can anyone give me one person, at least one person who is thrown out? Can you give me? No person is thrown out because this is the infinite hotel. Every person will go to the next room. Every person will go to the next room. Every person will keep going to the next room. Yes or no? Is this clear? Please tell me. Every person is going to the next room. So you can notice no person is evicted. No person is thrown out. Also, room number 1 becomes empty. If I do this, So this is your Hilbert's Grand Hotel. So you can notice, did you understand the following point? That intuition does not work with your infinite sets. This is the point I'm making. I just want to make one point, that intuition works with finite set. It does not work with infinite set. Yes or no? Is this clear? Please tell me. Intuition works with finite set. It does not work with infinite set. Infinite sets, they behave in a weird way. This is what I wanted to tell you. I hope you understood. Now let's see the next chapter, that is cardinality. Okay, let's see this cardinality, the next chapter. You already know what is cardinality of a finite set, yes or no? If I ask you what is cardinality of a finite set, that you already know. So for finite set, how will you find the cardinality? Please tell me. If I give you a finite set, let's assume I give you a finite set. This finite set S is I'm giving you. Tell me how to find the cardinality. How will you find the cardinality of S? How will you find cardinality of S? What you will do, if you want to find the cardinality of S, you will count how many elements are there. Agree with me? Okay, so for finite set, if you want to find the cardinality, what you will do, you will count the number of elements. You will count the number of elements, right? Agree? You will count the number of elements. This is how you will do. Number of elements in a finite set. This is what you will do. You will count the number of elements. This is what you will do. Okay, so very simple point. If you have a finite set, remember, if you have a finite set, then what the cardinality? If S is finite set, then the cardinality of S is the number of elements in S. We denote it by this symbol. Okay, so this is the definition of cardinality. If S is a set, now if there are exactly n elements, okay, means this is a finite set. If you have exactly n elements, then it means this is a finite set, and the cardinality, that will be n. If your set is not finite, then what you can say? If your set is not finite, set which is not finite, what you will say that? What we will call it? If a set is not finite, then what we call it? That is your infinite set. Yes or no? This type of set we will call it infinite set. If set is not finite, then that is infinite set. Okay, very simple. This is the idea of cardinality. For example, what is the cardinality of this set? What is the cardinality of this set? Odd positive integers less than 10. Odd positive integers less than 10. That is 5. What is the cardinality of this set? S is letter of English alphabet. So the cardinality will be 26. Okay. You can see the cardinality of empty set, that will be 0. Okay. If a set is, when can I say set is infinite? If it is not finite. Yes or no? For example, the set of positive integers, that is infinite. Yes or no? The set of positive integers, this set is infinite. This is infinite. When I say infinite set, what that means? Infinite set, that simply means not finite. Yes or no? This set is not finite. Is this clear? Very simple. Now tell me, this is what you are doing. If you want to find for finite set, remember, for finite set, if S is finite set, then to find cardinality, what you will do? You will count the number of elements. This is what you are doing. You will count the number of elements, right? Okay. Now tell me, you are counting the number of elements. You are counting the number of elements for finite set. For finite set, you are counting the number of elements to find cardinality. What about infinite set? If I give you infinite set, how to find the cardinality? For example, tell me what will be the cardinality of this set. I'm asking, what is the cardinality of this set? This is the simple question I'm asking. What is the cardinality of this set? See, this set is infinite, I agree. Why this is infinite set? This set is infinite because it is not finite. Okay, infinite set simply means not finite. This set is not finite. Now I want to ask you, what is the cardinality of this set? Will you count? Will this algorithm work? Will this algorithm work? Tell me. Count number of elements. Will this work? Count number of elements. Will it work? I'm asking a simple question. Count number of elements. Count number of elements. Will it work? Will this definition work? Okay. Will this work? This definition will not work. Yes or no? Can I say this definition of cardinality will not work? This definition of cardinality will not work for infinite set. Cardinality will not work. will not work for infinite set. Yes or no? For infinite set. If you have an infinite set, this definition will not work. So we need to change the definition. Agree with me? Yes or no? This definition will not work. Like you are counting the number of elements. You are counting the number of elements. This definition will not work. So you can see this definition of cardinality will not work for infinite set. So what we need to do? Tell me. You can see this definition of cardinality does not work for infinite set. Which definition? This definition. Please understand. This definition of cardinality. This will not work for infinite set. So what we need to do? In this situation, what we need to do? We need to change the definition of cardinality. Yes or no? We need to change the idea of cardinality. Is this clear? Now we will change it. We will change the idea of cardinality so that it works for finite as well as infinite. This is what we need to do. Okay, so we need to change the idea of cardinality so that it works. So that it works for finite as well as infinite set. For finite as well as infinite sets. As well as infinite sets. This is what we need to do. We need to change the definition of cardinality. The definition we need to change. We need to change the idea of cardinality so that it can work for finite as well as infinite set. Okay, so how to do that? See, right now, what is the definition of cardinality? That is counting. Yes or no, you are counting. Now, from counting to comparison. So remember, we need to change the idea of cardinality. This idea of cardinality, we need to change from counting to comparison. So far, we were counting. If you do this, will it work for infinite set? If I do this, if I count the number of elements, will it work for infinite set? No, it will not work. So we need to change the idea of cardinality from counting to comparison. Okay, we will compare. So from now onwards, what we will do? Remember, for infinite set, cardinality is not used to count the number of elements. Cardinality is not used to count the number of elements, but it is used to compare the size of two sets. It is used to compare the sizes of two sets. Is this clear? Simple point I'm telling you that for infinite set, cardinality is not used to count the number of elements. We will not count the number of elements. We will use it to compare the sizes of two sets. We will compare two sets, whether they have same cardinality. Basically, now what we will do from now onwards, what this cardinality is used like this. See, cardinality. Okay, cardinality, we will use it like this. If you have set A, set B, they can be any set, finite or infinite. They can be any set, remember, finite, infinite, whatever. Finite, infinite, whatever. Okay, so this cardinality, what we will do, we will use it as a comparison. This cardinality is used as a comparison. So we will use it. How we will use it? Used to compare. Used to compare sizes of A, B. Sizes of A, B. So we will not count the number of elements in A. We will not count the number of elements in B. What we will do? We will compare the sizes. We will find out, do they have same size? Do they have same size? Okay, do they have this type of situation? Do they have this type of situation? So basically, this is what we will check. Okay, this is what we will check. Do they have this type of situation? Do they have this type of situation? So this is what we will do now. Is this clear? Let me know. Did you understand the motivation? Did you understand the motivation? Please tell me. Because if you have an infinite set, then counting will not work. You are counting. For a finite set, you are counting. If I give you a finite set, you can count how many elements are there. Okay, to find the cardinality, you can count the number of elements. But remember, this will not work for infinite set. If I give you infinite set, you cannot count the number of elements. You cannot count the number of elements. So this cardinality, we will use it. We will use it to compare the sizes. Basically, for these two sets, we will compare the sizes. What comparison they have. Okay, what relationship they have. This is what we will do. Is this understood? So remember, cardinality that is used to compare the sizes of two sets. That is used to compare the sizes of two sets. You have two sets. Okay, this cardinality that is used to compare the sizes of two sets. Is this clear? Let me know. Is this understood? Please tell me. So you can see the cardinality of set. This is used to compare which set is bigger. Do they have same size? What the relative size of two set? This is what we use it. Okay, let's move on now. So the new definition of cardinality, what that will be? Now we are going to see the new definition of cardinality, that is to compare sizes of two set. What is that definition? That definition is like this. So tell me, when can I say two set have same cardinality? When can I say set A, set B, they can be any set. Remember, they can be any set, finite, infinite, any set. When can I say they have same cardinality? Finite set, infinite sets. They can be any set. Remember, these two, they can be any set. So when can I say they have same cardinality? Please tell me, what is the definition? When can I say A cardinality is equal to B cardinality? If and only if there exists a bijection. Very good. If and only if there exists a bijection. If you can create a bijection. If you can create a bijection between A, B. Between A, B, if you can create a bijection. If you can create a bijection, then they will have same cardinality. So this is what I'm saying. New definition of cardinality to compare the sizes of two set. So that we can compare the sizes of two set. Okay. So to compare, this is the new definition. You can notice two set have same cardinality if and only if there exists a one-to-one correspondence. There exists a bijection. In this situation, we will say they have same cardinality. This is the definition. Okay. So two set, they have same cardinality if and only if there exists a bijection between them. For example, see this. Can you say they have same size? These two set, can you say they have same size? Let me know. These two set, can you say they have same size? How to prove it? How to prove they have same size? This set, they have same size. How to prove it? How to prove it? By giving a bijection. Yes or no? If you can create a bijection, then you can say they have same size. Can you create a bijection? Can you create a bijection? Between these two sets, can you create a bijection? Yes, of course, you can create a bijection like this. You can create a bijection like this. So because there exists a bijection, so this set A size, this is your set A, this is your set B. Remember, because there exists a bijection, because there exists a bijection between A, B. Between A, B, there exists a bijection. So what you can say? So their cardinality is same. So their cardinality is same. Is this clear? So their cardinality will be same. Please tell me, did you understand this? Because there exists a bijection between these two, this set and this set, there exists a bijection. So I can say they have same cardinality. Okay. What about these? So you can see, this is the idea. This is the definition. Two set have same cardinality if you can put their elements in one-to-one correspondence. That is bijection. Okay, like here, this set, you can put their elements in a one-to-one correspondence. So they have same cardinality. What about these two sets? Is there any bijection? Can you create a bijection between these two? Between these two sets, this set, can you create a bijection? Try to create a bijection. Is it possible? Give me one bijection. Give me at least one bijection. At least one bijection. No bijection possible. Yes or no? This set, no bijection possible. So because no bijection possible, so they have different cardinality. Yes or no? Yes or no? Because no bijection possible, so I can simply say that they have different cardinality. So remember, this is your set A, this is your set B. Now remember, because I can say this, because there is no bijection, you cannot create any bijection. Because there is no bijection between A, B. So what I can say? Between A, B. So what I can say, tell me. There is no bijection. So what I can say? I can say that they have different cardinality. Their cardinality is different. Okay. So quite simple. I hope you understood all these things. So remember, two sets have same cardinality if you can create a bijection between them. Okay. If you can create a bijection. If there exists a bijection from A to B. If there exists a bijection from A to B or from B to A or between A, B. If you can create a bijection. So if you can create a bijection, immediately you can say they have same cardinality. So remember, this is the simple point. Note, you have two set A, set B. Okay, set A, set B. They can be any set, finite or infinite. They can be any set. Remember, they can be any sets. They can be finite, they can be infinite. It does not matter. Okay, you can take whatever sets you want. So you can see these are two sets. Now, if I can create a bijection, tell me, simple question I'm asking. If there exists a bijection, if I can create a bijection between them, then do you agree they will have same size? If there exists a bijection between A comma B, or I can say from A to B, if there exists a bijection, then tell me, there exists a bijection. What that means? Bijection means this is your set A, this is your set B. What bijection means? A1, A2, A3, and so on. B1, B2, B3, and so on. Bijection means one-to-one correspondence. One-to-one fight, one-to-one fight, one-to-one fight, one-to-one fight. So if you have this type of bijection, if there exists a bijection, then you will say they have same cardinality. They have same size. They have same size. Yes or no? Because bijection means what? Bijection is one-to-one fight. Yes or no? What is bijection? Just tell me. If I give you a bijection between A comma B, or I can say from A to B, if I can give you a bijection, then what that means? That means one-to-one fight. Bijection means one-to-one correspondence. Remember, bijection means one-to-one correspondence. This is the another word for bijection. One-to-one correspondence. One-to-one correspondence. So for example, one-to-one fight. Everyone in this set A will fight with unique person here. And remember, every person here will fight with unique person here. It's like, for example, India army, China army. Okay, there is a one-to-one fight, one-to-one correspondence. So can I say they have same size? Means everyone here is fighting with unique person here, and everyone here is fighting with unique person here. So this type of bijection, if you have this type of one-to-one correspondence, then what I can say? Then I can say they have same cardinality. Okay, these two sets, they have same cardinality. Okay, now let's see something very interesting. Again, I want to tell you that finite set, infinite set, they behave in a different way. Let me again give you one example. Okay, let's see for which intuition will work. Your intuition, will it work for finite or intuition? Intuition works. Let's see for finite or infinite. Let's see. I will give you one more very interesting example. I will give you for finite sets, not for infinite sets. Not for infinite sets. Okay, let me prove it to you with one more very interesting example. You tell me a simple point. This is my question. Let's assume you have finite set A comma B. You have two finite sets A comma B. These are two finite sets. Now let's assume that this type of situation is there, that A is subset of B. Let's assume I'm giving you A is subset of B, and there exists an element X which belongs to B but does not belong to A. Okay, in this situation, what you can say about their cardinality? Did you understand the question? You have finite sets. These are finite sets A comma B. Okay, so that A is subset of B. A is subset of B. There exists an element which belongs to B, does not belong to A. In this situation, what you can say about cardinality of A, cardinality of B? What you can say about them? In this situation, the answer will be A cardinality will be less than B cardinality. Yes or no? Simple. Because very simple. Remember, you have this set. Okay, this is your set A, this is your set B. This is the set A, this is the set B. But there is at least one extra element in B. There is at least one extra element in B. Yes or no? There is at least one extra element in B. So in this situation, I can say set A cardinality will be less than equal to set B cardinality. Because remember, every element of A that is already in B, agree with me? Every element of A that is already in B, but B has some extra elements. Yes or no? B has some extra elements. So please understand, every element of A that is already in B, but B has some extra elements. Okay, so I can say cardinality of A will be less than equal to cardinality of B. Now tell me the same thing. For these two sets. Now tell me the same thing for these two sets. Means whole numbers and even whole numbers. Which set is bigger? Set of whole numbers, which of them is bigger? See, some of you might be thinking, this is what you are thinking, right? Some of you might be thinking, whole numbers are these. See. You are thinking like this: 0, 1, 2, 3, 4. Okay. And even whole numbers are these. Even whole numbers are 0, 2, 4, 6, and so on. So what you are thinking? You are thinking that, see, you are thinking like this. You are thinking like this, that every element of E that is already in W. Yes or no? You are thinking like this. Agree with me? You are thinking like this. Every element of E that is already in W, but W has some extra elements. Yes or no? W has some extra elements. Do you agree with me? W has some extra elements. Every element of E that is already in W, but W has some extra elements. So can I say W cardinality will be greater than E cardinality? Can I say? So can I say this? That W cardinality that is greater than E cardinality? Can I say W is bigger? Remember, every element of E that is already in W, but W has some extra elements. Infinite number of extra elements. How many extra elements W has? How many extra elements W has? Infinite number of extra elements. Yes or no? So can I say that W cardinality that is greater than E cardinality? If you are thinking like this, then let me tell you this is wrong. Okay, let me tell you this is wrong. Okay, this is wrong. ये है आम जिंदगी. Okay, you know there is a ad. Have you seen that advertisement? ये है आम जिंदगी. ये है आम जिंदगी. So what will come now? What will come now? Now will come the Mentos zindagi. Yes or no? ये है आम जिंदगी. If you are thinking like this, this is okay. No problem. If you are thinking like this, then this is आम जिंदगी. ये है आम जिंदगी. You can say like this. Okay, just say ये है आम जिंदगी. Now will come Mentos zindagi. But remember, this is wrong. This thinking is wrong. Okay. Now let's see the Mentos zindagi. Okay. Now I will tell you the Mentos zindagi. So now let's see the Mentos zindagi. I want to ask you a very simple question. A very simple question I want to ask you. If I can do this, a simple question. I'm asking if I can do this, that one-to-one correspondence, if I can create, will you agree with me? They have same size. See what I'm asking. Please understand what I'm asking. If I can create a one-to-one correspondence, means for every element here, there is a unique element here. For every element here, there is a unique element here. For every element here, there is a unique element here. For every element here, there is a unique element here. If I can do this, then will you agree with me that they have same size? If I can do this, simple question I'm asking. Just apply the intuition now. Apply your intuition now. If I can do like this, that for every element here, I give you unique element here. And for every element here, I give you unique element here. If I can do this type of one-to-one correspondence, if I can give you, will you agree with me that they have same size? If, this is what I'm saying, if there exists a one-to-one correspondence, simple question I'm asking, if there exists a one-to-one correspondence, one-to-one fight, if I can give you one-to-one correspondence between W, E, then will you agree with me that they have same size? Okay. Between this army, this is an army. Okay, consider this as army. Between this army, if I can create a one-to-one fight, okay, every person here fighting with unique person here, every person here fighting with unique person here, one-to-one fight I can create. I can create a one-to-one fight. If I can create this type of one-to-one fight, then will you agree that they have same size? Okay, now let's see. Can you create a one-to-one fight between these two? Simple. See, very simple. This is your set W. This is your 0, 1, 2, 3, 4, and so on. This is your set E. This is 0, 2, 4, 6, and so on. Now, just consider this mapping. Consider this fight. Just consider this fight. Okay, just for a moment, just consider this fight. Is this fight from W to E? Is this fight bijection? Is this one-to-one fight? Consider this fight. Okay, in this fight, what I'm doing? N is fighting with whom? N is fighting with 2N. N is fighting with 2N. Yes or no? Remember, this is a fighting from W to E. This is a fighting from W to E. And N is fighting with 2N. Okay, this person N, this is fighting with 2N. Is this injective? Simple question I'm asking, is F injective? Is F injective? Is F 1 to 1? 1 to 1 means injective. Is F injective? 1 to 1 means injective. So tell me, is F injective? The answer is yes. Yes or no? Because every two different elements have different images. Agree? Yes or no? The answer is yes. Why this is injective? Because you can notice. Tell me. A simple question I'm asking. If FA equal to FB, what that will mean? What that will mean? FA equal to FB. What is FA? What is FA? What is FA? That is 2A. What is FB? That is 2B. Okay. So you can notice 2A equal to 2B. That implies what? That implies A equal to B. This is the definition of injective function. This is the definition of injective function. So this function, notice this function is injective. Yes, correct. Notice this mapping, this fight. This fight is injective. This fight is injective. Is this fight surjective? Is F surjective? Tell me. Is F onto? Means for every element in E, is there a pre-image? For example, if tell me a simple question I'm asking. If Y belongs to E, then what will be the image? What will be the pre-image? Y belongs to E. What will be the pre-image? Tell me. What will be the pre-image? Pre-image will be Y by 2. Yes or no? Pre-image will be Y by 2. So this is onto also. Every element of E is covered. Can you notice? For example, this element, if I give you this element, like for example, let's assume 500. Who will fight with 500? Who will fight with 500? 250 will fight with 500. Yes or no? This will fight. Yes or no? Very simple. So if for all Y, whatever Y I give you, what is the pre-image? The pre-image is Y by 2. The pre-image is Y by 2. So this is onto also. So this is 1, 1 also. This is onto also. So can I say this is bijection? So remember, this F is 1, 1 also. F is onto also. So what I can say? So I can say F is 1 to 1 correspondence, right? Yes or no? F is 1 to 1 correspondence. Please tell me. F is 1 to 1 correspondence. So remember what is happening here. Please notice what is happening here. Every element here is fighting with unique element here. Every element is fighting with unique element here. Yes or no? Is this clear? This person is fighting with this person. This person is fighting with this person. So can I say there is 1 to 1 correspondence? Please understand, there is a 1 to 1 correspondence. So can I say that they have same size? Now can I say there is same size? Now can I say they have same size? 1 to 1 correspondence. So now I can say they have same size. So remember, these two sets, they have same size. Is this clear? Let me know. So the question was simple. The question was simple. Do they have same size? So remember, there exists a bijection. There exists a bijection between W, E. You can create a bijection between W, E. So what I can say? So they have same size. So this is a very weird result. Yes or no? This is a very weird result. This is more weird than Hilbert Grand Hotel. In the Hilbert Grand Hotel, you have a fully occupied hotel. In a fully occupied hotel, you are accommodating one guest. Okay. This is more weird than that. Agree with me? You can notice that this W, the set of whole numbers is like this: 4, 5, 6, 7, 8, and so on. This is set of whole numbers. And remember, this is set of real numbers. This is set of even numbers. This is set of even numbers. But still they have same size. Still remember, the size of whole numbers, that is same as the size of even whole numbers. Please tell me how many of you got it? Because there exists a bijection. Because you can put them in 1 to 1 correspondence. Okay, because remember, you can put them in 1 to 1 correspondence. W, E. These elements, you can put them in 1 to 1 correspondence. You can put them in 1 to 1 fight. Because you can put them in 1 to 1 fight, so they have same cardinality. So remember, the size of whole numbers, that is same as size of even numbers, even whole numbers. Now, do you agree that infinity does not work with your intuition? Yes or no? Now, do you agree that infinity does not work with your intuition? For example, what intuition says? For finite sets, your intuition can work. If you have finite sets, for example, let's assume this is your set A, this is your set B. Okay, let's assume this situation you have, then in this situation you can immediately say that set A cardinality is less than set B cardinality. Okay, but remember, can you say the same thing for infinite sets? Can you say the same thing for infinite sets? The same logic can you apply for the infinite sets? For the infinite sets, tell me. But here you can notice the set of whole numbers, the size of these two sets, they are same. They have same size. Okay, so for infinite set, apply the definition. What you are going to do now? From in future, what you will do? For infinite sets, what you will do? For infinite sets, what you will do? Just apply definition. Apply definition. You know, bijection, injection, these definitions you apply. So apply definitions. Don't apply your intuition. Don't apply your common sense. Apply definitions. And what are the definitions? Bijection, injections, these definitions you apply. Okay, bijections, injections, surjections, these definitions you apply. I hope you understood. Please tell me. For infinite sets, don't apply your common sense. Don't apply the common sense. Okay, because you can see here, this is your set of whole numbers. These are actually set of whole numbers. Tell me why set of natural number has 0? What is the reason? See, set of natural number has 0. Why? Because some authors, they include, yes or no? Some authors. There are some authors, they include 0 in the natural numbers. Okay, but actually this is the whole number. This is author dependent. I told you this point. I told you that 0 belongs to nature. Some authors, what they do? Some authors, what they do? Okay, some authors, they do that 0 belongs to natural number. And some authors, what they do? They say that 0 does not belong to natural number. 0 does not belong to natural number. In your whole life, which convention you have studied in your whole life? From your first class, or I can say from your 4th, 5th class, which convention you have seen? This is what we will follow. Okay, this is what we follow, because we have seen this convention from our childhood. Okay, this is what we follow. In our childhood, we have seen this. Okay, so anyway, so you can easily notice this is actually the set of whole numbers. So you can see set of whole numbers, set of even whole numbers, they have same size. They have same size. Remember, they have same size. Yes or no? Did you notice they have same size? Because you can put them in one-to-one correspondence. You can put them in one-to-one fight, one-to-one correspondence. So they have the same size. Let's move on now. So apply the definitions for infinite sets. Apply these definitions: bijection, injection, surjection. Now tell me this point. Set of whole numbers, set of integers, means set of non-negative integers and set of all integers. Which is bigger? Which set is bigger? Please tell me. Simple question. Let me know. Which is bigger? Set of non-negative integers, set of integers. Which set is bigger? Again, they have same size. Can you create a bijection? See, this set of whole numbers, that is like this: 0, 1, 2, 3, and so on. And set of integers that has 0, 1, 2, 3, you have 0, 1, 2, 3, you have. You also have negative numbers, -1, -2, -3, and so on. So you have these. Okay, so you can easily notice every whole number is an integer, right? Agree? Every whole number is an integer. Every whole number is integer, but you have extra elements here. You have extra elements here. But still, you can prove that they have same size, because you can put them in one-to-one correspondence. Can you put them in one-to-one correspondence? Can you put them in one-to-one correspondence? Can you put them in one-to-one correspondence? Means from integers to whole numbers, can you give me one-to-one correspondence? Some students is saying fx equal to minus x. Will it work? Fx equal to minus x. Will it work? Will it work? Please tell me. Fx equal to minus x. This is not even a function. This is not even a function. This is not even a function. Why this is not even a function? Tell me. This is not even a function. Why? What is the reason? What is the reason this is not even a function? Because you can notice F2, that will be -2, that does not belong to W. Yes or no? F2 will be -2, that does not belong to W. So this is wrong. Okay, this is not even a function. Forget about everything else. This is not even a function. Some student is saying fx equal to absolute value of x. Will it work? Fx equal to absolute value of x. Will it work? This is a function. This is a function, but this is not injective. This function is not injective. So this will not also not work. This is not injective. This function is not injective. You can notice f2, f-2, they have same image. f2, f-2, they have same image. This is not injective. Okay, so this will also not work. This will also not work. So tell me, so can I stop and can I say that there is no bijection? Can I say there is no bijection? Can I say there is no bijection? Tell me. No, try something else. Try something else. Okay, let me try. Okay, let me try. See how I will do. Okay, notice, please notice what I will do. These are the integers. These are the whole numbers. See what I will do. These are the whole numbers. 0, 1, 2, 3, 4, 5, and so on. These are the whole numbers. So first what I will do. First I will put very simple. That 0 I will put here, 1 I will put here, 2 I will put here, 3 I will put here. So like this, what I will do. See, notice, very simple. What I'm doing. First I'm taking care of positive integers. Yes or no? Now, where I will put the negative integers, I will put them here. I will put them here. Is this clear? See what I'm doing. This type of mapping I'm creating. I'm creating this type of mapping. This type of mapping I'm creating. See, this is a very natural mapping, right? Sometimes you write like this. Have you written integers as this? Have you ever written integers like this? Tell me. In your life, have you ever written integers like this? Of course, sometimes we write like this. This is integers, right? You can write like this. Some people, they write like this, dot, 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 then 0. Okay, dot, like this, -2, -1, 0, 1, 2, and dot, dot, dot. So like this, people write like this. Yes or no? So this is what I'm saying. Is this set of integers? 0, -1, 1, -2, 2, -3, 3. Anyway, this is a set. Order does not matter. Yes or no? These things are set. These things are set. Order doesn't matter. Unordered. These are unordered. Order doesn't matter. Yes or no? So you can write them in this order. So this is what I'm saying. You just write like this. Yes or no? These are set. This is set of integers. You can write anyway. This is a set. This is unordered. You can write whatever you want. Yes or no? So very simple. This is what I'm saying. This type of mapping I'm creating. In this mapping, did you notice what is happening? Did you notice in this mapping what is happening? In this mapping, what I'm doing? This is what I'm doing, that if n is greater than equal to 0, what is fn? See what I'm doing. Fn. Okay, fn. If n is greater than equal to 0, what is fn? That is 2n, right? Yes or no? Very simple. If n is greater than equal to 0, for example, this is greater than equal to 0, I'm mapping to 4. Okay, remember, this is from integers to whole numbers. Okay, if n is less than 0, then what I'm doing? Tell me. If n is less than 0, what I'm doing? If n is less than 0. So for example, this -2, this is mapping to 3. -3 is mapping to 5. So I'm doing minus of n plus 1 by 2. Okay, see. No, here what we are doing, 1 is mapping to 2, 0, -1, -2. So here what we are doing, minus of n minus 1 by 2. Will it work? So here what we are doing, -2 is mapping to 3, -3 is mapping to 5. So every n, that is mapping to whom? -2 and -1. minus of, is this correct? Let me know. No, this is not correct. I think this will work. Yes or no? Minus 2n plus 1. Will it work? Let me know. So for example, this minus 2, you can see, if I put n equal to minus 2, I put n equal to minus 2, then what I will get? I will get minus 3. If I put n equal to minus 3, if I put n equal to minus 3, then I will get 5. Sorry, again, I'm getting minus 5. Okay, bracket of minus 2 plus 1. I think this will work. Okay, if I put minus 2, then I will get minus 2 I'm putting. So that is minus 4 plus 1. That is minus 3. Yeah. Okay, so yeah, this will work. Yes or no? Minus of, so that is minus 2 minus 1. Yeah, that is working. Yes or no? Minus of 2 and plus 1. So for example, if I put n equal to minus 1, if I put n equal to minus 1, this is working. Yes or no? Is this clear? Please tell me. This is working. Okay, yes or no? See here. Okay, so yes, this is actually working. You can just check. This is actually working. You can check. So this is what I'm saying. Please notice. I am creating a bijection from Z to whole numbers. From Z to whole numbers. These are the Z. These are whole numbers. Okay, and I'm creating a bijection. I'm creating a bijection like this. See, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Dot, 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 dot. Here, what I'm doing like this. If you have a, if n is greater than c, this is what I'm doing from integers to whole numbers. Remember, from integers to whole numbers. What I'm doing like this. If your n is already greater than equal to 0, what I will do with that? For example, 0, for example, 1, for example, 2, for example, 3, for example, 4. If your n is already greater than equal to 0, what I will do with that? I will map it to 2n. Yes or no? I will map it to 2n. If your n is already greater than equal to 0. And if your n is less than 0, if your n is less than 0, like minus 1, minus 2, minus 3, minus 4, if your n is less than 0, then what I'm doing? I'm doing like this, minus of 2n plus 1. Is this clear? Please tell me. Minus of 2n plus 1. I hope you understood the idea. See, this is the simple idea. From integers to whole numbers, from here to here, I'm creating a mapping and I'm saying that f of n. Remember, n belongs to integers, right? Yes or no? This is coming from integers because your domain is integers. And your codomain is this is the codomain, that is the set of whole numbers. Now, what we are doing? We are saying that if n is already greater than equal to 0, then you map it to 2n. And if n is less than 0, then you map it to minus 2n plus 1. Okay, you can check. Please notice. For example, if n is minus 1, what will be the mapping? If n is minus 1, what will be the mapping? Please tell me. That will be minus of 2 into minus 1 plus 1. Yes or no? 2 into minus 1 plus 1. Tell me what that will be. Overall, that will be 1. Yes or no? For example, if n is equal to minus 3, tell me what fn will be. If n equal to minus 3, if n equal to minus 3, what fn will be? If you put n equal to minus 3, n equal to minus 3, then fn will be 5. Yes or no? And this is what we are doing. So you can notice this is mapping to 1. You can see this is mapping to 1. This is mapping to 3. This is mapping to 5. This is mapping to 7. Did we get a bijection or not? Please tell me. Yes or no? We got a bijection because whatever number you take, this 1-to-1 correspondence you got. Yes or no? This 1-to-1 correspondence you got. We got a bijection. Is this clear? Please tell me. Why this is a bijection? Let's check. Let's check why this is a bijection. Simple question I'm asking. First of all, you tell me, is this onto? I'm asking, is this onto? this function, I have created this function. Is this function onto? I have created this function f. Is f onto? Is f onto? Can you say for every element there is a preimage? Can you say for every element there is a preimage? Yes. For example, if you take an even number, what will be the preimage? If you take an even number, what will be the preimage? If you take an even y, what will be the preimage? What will the preimage? Tell me. If you take an even y, okay, then what will be the preimage? Even y from W. Then the preimage will be y by 2. You can notice the preimage will be y by 2. You can just simply see. If you take even y, the preimage will be y by 2. Yes or no? And what about odd y? If you have odd y, then what will be the preimage? If your y is odd, then what the preimage? Tell me. If you take a odd y, then what will be the preimage? Let me know. Then that will be very good. See, because if you have odd y, if your y is odd, then I can say that this equation was used. Correct? If your y was odd, for example, fx equal to y, and let's assume this is odd, and let's assume this is odd. Okay, then in this situation, it means this equation was used. Remember, this will always give you even. Do you agree? This equation will always give you even. This will always give you even. So if you are getting a y, which equation was used? Tell me. If you are getting a y, which equation was used? This will always give you odd. Correct? This is what I'm saying. So I can say fx equal to minus of 2x plus 1 is equal to y. So from here, if you notice, what is x? What will be x here? Let me know. So x will be y plus 2 by 2 minus of y plus 1 by 2. Yes or no? Is this clear? So I can say the preimage will be minus of y plus 1 by 2. This is the preimage. So can you notice every element has a preimage? So is f onto? Answer is yes. Is this clear? Please tell me. See, this is not complicated. This is not complicated. Please notice what I'm saying. You have a f from integers to whole numbers. Okay, remember, this is your domain. This is your domain. This is your codomain. Just take your copy pen. This is not complicated. Now, what we are doing, we are defining this function like this, that fn is equal to, image will be 2n if n is greater than equal to 0. And image will be minus of 2n plus 1, minus of 2n plus 1 if n is less than 0. Now, you can notice one thing. This image is always even. Do you agree? This image is always even. This number is always even, 2n. And you can note this image is always odd. This number is always odd. So if you are getting an odd image, then from where that must have come? For example, I am saying that if let's assume you have some number 11, then who is the preimage of this? If I ask you, for this 11, who is the preimage? Let me know. Who must have been the preimage? So if you are getting 11, this image you are getting. If you are getting this image, odd image you are getting odd image, then definitely this must come from here, because this will give you even number. This will give you even image. I can say this is even image and this is odd image. So if you are getting 11, then I can say fx equal to 11, and this fx must have come from this must have come from minus 2x plus 1 equal to 11. So from here, x is equal to minus of 11 plus 1 by 2. Okay, that is what? Minus of 11 plus 1 by 2. That is minus 6. So here I can say x is minus 6. Yes or no? So you can notice here this x is minus 6. So finally I can say your answer will be minus 6. I hope you understood this. So this is what I'm saying, that every element has a preimage, right? Yes or no? In this function, every element has a preimage. What about 1, 1? Is this function 1, 1? Is this function injection? Is this injection or not? Tell me. This function, is it injection? And again, the answer is yes. Can you notice one thing? Will they ever I can say overlap. Will they ever overlap? Let me know. These two, will they overlap? See, this will give you even image. Okay, this will give you even image. This will give you even image, and this will give you odd image. So they will never overlap. Can you notice? They will never overlap. First of all, they will never overlap. And you can easily notice here, will any two number, will they get same image? Here, just focus here. See, these two things will never overlap. These two things will never overlap. They will never overlap. Now tell me, here within this, for n greater than equal to 0, can you get same image for different elements? N greater than here, can you get same image for different elements? Same image for different elements? No. Here, can you get same image for different elements? Again, no. So this is injection. So this is bijection. And because bijection exists, so integers and whole numbers, they have same size. Integers and whole numbers, they have same size because bijection exists. So they have same size. I hope you understood. See, in future, if you want to prove that these two, okay, if you want to prove that there is a bijection, if you want to give bijection between W, Z, how will you give? Bijection between W, Z, how will you give? If you want to give bijection between W, Z, very easily you can give like this. See, okay, very simple. This is Z, this is W. Okay, just write like this. -2, 2, -3, 3, -4, 4, and so on. Okay, and write like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. That's it. So this bijection you can give. I hope you understood. This is the bijection you can give between Z, W. Okay, is this clear? Let me know. Is this understood? So this is the simple proof that there is a bijection. So can I say, because there exists a bijection? See, this is the bijection between W. This is your W, between W, Z. So can I say they have same cardinality? Yes or no? They have same cardinality. You can notice. Is this clear? Please tell me. Let me know. Okay. So this bijection is actually given from N to Z. From N to Z, this is given. Okay. This is given from N to Z. We have given from Z to N. Yes or no? We have given from Z to N. They have given from N to Z. That is fine. That is fine. They have given from N to Z. And we have given from Z to N. We have given from Z to N. So this you can see. This is the bijection. Okay. From Z to W we have given. Okay. Let's just see one last question. Can you answer this question? Tell me the answer for this question. Set of whole numbers W and set of powers of 2. Which is bigger? Which is bigger? See, set of whole numbers. This is set of whole numbers. And now I am asking set of powers of 2. Powers of 2 means 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, and so on. Which is bigger? How can you say they are same? How can you say they have same size? See, this is your W and this is your powers of 2. Here you have, for example, 1, 2, 4, 8, 16, 32. And here you have many extra elements. For example, here you have 3, 5, 6, 7, 9, 10. How can you say? Can I say every element here is here? Can I say every element is here is here? Can I say every element that is here also? Yes. But there are some extra elements. There are many extra elements. So how can you say they have same size? How can you say they have same size? Yes, they have same size because there exists a bijection. Because you can put them in, because we can create a bijection. There exists a bijection between them. There exists a bijection between W, P. Okay. Set of, you can say like this, non-negative powers. Here you can say non-negative powers. Okay, set of non-negative powers. You can say like this. So you can put them in bijection. What bijection you will give? Tell me. What bijection you will give? Let me know. From W to P, can you give me some bijection? This is your W, this is your P, this is your 0, 1, 2, 3, 4, 5, and so on. And this is your 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, and so on. Yes, this simple bijection you can give. Yes or no? Very simple. This simple bijection you can give. So you can give this bijection Fn equal to 2 power n. Can you notice this is bijection? Can you notice this is bijection? Yes or no? This is a bijection. Is this clear? This is a bijection. Let me know. Is this understood that this is a bijection? Please tell me. Is this understood that this is a bijection? Okay. So I hope you understood that they also have same size. These two, they also have same size. You can check it out. Okay. So I hope you understood everything that we have seen so far, whatever we have seen. So please understand these things we have seen. Everything that we have seen in this lecture, did you understand? Are you getting some idea of what is infinity? Infinity is weird, but if you apply the definitions, then that is easy. See, two things you must be thinking. I hope you are thinking two things. That yes, infinity is weird. Intuition does not work with infinity. But, if you apply the definition, if you apply the concept, mathematical concept, if you apply bijection, injection, surjection, if you apply these definitions, then infinity is also very simple. Yes or no? Yes or no? And you can easily prove many results. A lot of different, I can say a lot of weird results you can easily prove if you apply the bijection, injection, surjection, these definitions. If you apply, please tell me, did you found infinity interesting? That infinity is really interesting? Yes or no? Let me know. So far, whatever we have seen, are you comfortable with that? Okay. So the remaining things we will see in the next lecture. But before that, I just want to tell you these things are important. Okay. Before we go, I just want to tell you that the following things that we have already seen, these are important. Make sure you understand all the following theorems. Okay. Make sure you understand every following theorem. For example, are you comfortable with this theorem? One by one, I'm asking. Read this and tell me, are you comfortable with this theorem? Please tell me, did you understand this theorem, this definition? Did you understand this definition? If S, T are set, they can be finite, infinite, any set. They have same cardinality if and only if there exists a bijection between them. Yes or no? This is your first theorem. There exists a bijection between them. Then I can say they have same cardinality. Okay, very good. What about this next one? Did you understand this theorem? Did you understand this definition? If S, T are two set, finite or infinite, set S cardinality is less than set T cardinality if and only if there exists an injection from where to where? There exists an injection from where to where? From S to T. From S to T. And did you understand this? Read this theorem. This definition you read. S, T are two set, finite or infinite. When can you say that set S cardinality is greater than equal to set T cardinality? When there exists a surjection from S to T. What about this next one? Did you understand this theorem? Read this. Set S cardinality that is greater than equal to T cardinality if and only if there exists an injection from where to where? See, this T cardinality, this is less than equal to S cardinality. So there exists an injection from T to S. From T to S. Very good. Did you understand this theorem? This definition, did you understand? This mathematical concept, did you understand? S, T, they can be any set, finite, infinite. When can you say S cardinality that is less than equal to T cardinality? That means there is a surjection from T to S. There exists a surjection from T to S. And what about this? Did you understand this? That if A is less than equal to B and B is less than equal to A, what you can say? If this happens, then what you can say? If this happens, then A is equal to B. Then A is equal to B. The same thing is happening here. S cardinality is less than equal to T cardinality and S cardinality is greater than equal to T cardinality if and only if they have same cardinality. Yes or no? So all these things. Comfortable? How will you prove this? Let me know. Tell me quickly. How will you prove this? That S cardinality is less than equal to T cardinality. How will you prove this? To prove what you will do? you will create injection. You will create injective function from S to T. You will create injective function from S to T. From S to T, you will create injective function. Very good. Okay, create an injective function from S to T. How will you prove this? How will you prove this? Let me know. If you want to prove this, create injective function from where to where? Again, you create injective function from T to S. From T to S. Okay, from T to S, you can create injective function. Create an injective function from T to S. Very good. Okay, and how can you prove this? That they have same cardinality? Either you can give method number one, that is, you can give a method number one, create bijection. Create bijection. Just create a bijection between S comma T. Okay, either from S to T, create a bijection from S to T or T to S. Or T to S. Or create bijection from T to S. That is your choice. Okay, that is your choice. Or what you can do, or what is another method? Method number two. What is that? That is that if you want to prove this, you can do separately. You can do this and this. What you can do? You can prove that this cardinality is less than this cardinality, and you can prove this cardinality is less than this cardinality. To prove this, you will create injection from S to T. Okay, you will create injection. You will create injective function from S to T. You will create injection from S to T. From S to T. And if you want to prove this, then what you will do? If you want to prove this, what you will do? You will create injection from where to where? You will create injection from where to where? From T to S. Okay, so very simple. So like this you can do. All these things we have done. Okay, so I think, and you can notice set of integers. Set of integers, that is same as set of size of set of integers, that is same as set of whole numbers. So these are some counterintuitive results. Your intuition will not work here. You will be thinking, how can this happen? Every whole number is integer, but there are many extra integers. How can this happen? But this will happen because you can put them in one-to-one correspondence. You can put them in one-to-one correspondence, you can put. So that is the reason they have same size. Thus, okay, so I can also say number of integers. Okay, how many integers you have, that is same as how many whole numbers you have. Agree? How many integers you have, that is same as how many whole numbers you have. The size of whole numbers, that is same as size of integers. Okay, so these things we have seen. I hope you are comfortable, and the remaining things we will continue in the next lecture. So tell me, anyone has any doubt in this class? In this lecture, do you have any doubt? Let me know. We will continue in the next lecture. If anyone has any doubt in this lecture, please let me know. This countability is very interesting, let me tell you. And many tricky questions can be created. You can notice a lot of tricky questions they can create. But don't worry, by the end of countability, you will understand infinity. Okay, you will understand this infinity, and also you will be able to solve every question they can ask you in the GATE exam. Whatever question they can ask you, we will cover. Okay, so thank you, everyone. Is there any doubt? Okay, so see you in the next lecture. Thank you. So Joe is asking, for infinite set, do we need to redefine the cardinality definition? Joe, we have already redefined. Yes or no? For infinite set, we have already redefined the cardinality definition. All the definitions that we have seen, these are mathematical definitions. Okay. So we have, for infinite set, we have already redefined the definition of cardinality. Okay. So don't worry, in the next lecture, everything will become more clear. If there is some confusion in this lecture, if there is some confusion in the next lecture, everything will become more clear. Okay. So thank you so much. See you in the next lecture.